Should we just get started? Okay. All right. Thanks, everybody, for coming back for our afternoon session. I'm going to help moderate this. So we have kind of three different subsets of talks this afternoon. The first one is on parameter uncertainty and calibration and neon and single point. Lots of exciting things. So we're going to get started with an in-person talk by Claire Zarakis on land parameter uncertainty impacting the mean climate state. Can you hear me okay with the mic? All set? Okay, great. So today I'll be talking about how land parameter uncertainty impacts the mean climate state. And before I get started, I wanted to acknowledge our funding for this project and all of the many collaborators, I think all of whom are here in person or online today. So that's exciting. After the CGD seminar, I don't think I need to give a lot of motivation for why land parameter uncertainty is really important to grapple with as a community. We need to think about land parameter uncertainty in terms of our process understanding of how land interacts with the Earth system, and it's also really important for uncertainty quantification and model calibration. And we also know that changes to the land surface in general can generate really substantial climate responses. This figure is showing one example of this from Marisa Lugu's work, looking at the influence of evaporative resistance changes on surface temperature. But there hasn't been very much work connecting these two areas. So even though land models were first developed to provide lower boundary conditions for the atmosphere, when we think about the implications of land parameter uncertainty, we're commonly thinking about it from a framework in which the atmosphere is a fixed external driver and land changes can't influence the atmosphere. So I'm working on understanding the implications of land parameter uncertainty in a coupled context. So I'm asking two questions through this project. One, to what extent can land parameters influence the atmosphere? And secondly, how do atmospheric feedbacks modulate land parameters' influence on terrestrial processes? And for the sake of time today, I'm just going to address this first question, but I'm happy to discuss both later. So to answer these questions, I ran a coupled parameter perturbation ensemble, which was based off of the results of the CLM5 PPE project, which was discussed earlier today. So based on the results of that work, I selected 18 land parameters that had the biggest impact on land to atmosphere fluxes of water, energy, and momentum in that offline ensemble. And I also chose parameters so that we sampled different functional areas of CLM5. So these are parameters related to things like soil hydrology and various aspects of plant physiology. I'll get into the details of what the parameters are a little later. And I ran an ensemble of one-at-a-time simulations where I perturbed each of these 18 parameters to the same minimum and maximum values used in the CLM5 PPE. And I ran CESM2 that was coupled to the atmosphere, so using CAM6, CLM5, and a slab ocean under pre-industrial conditions. And I ran these simulations for quite a long time, so 140 years, so we really got to an equilibrium climate state. And in our ensemble, we found that these land surface parameter perturbations can generate really substantial spreads in land surface temperature. So at some latitudes, parameter perturbations led to up to a 3 degrees Celsius range in land surface temperatures. And when we averaged globally, our ensemble yielded a 2.2 degree spread in global mean land temperature and a 1 degree spread in global mean temperature, including both land and ocean. So for comparison, that's about a third of the spread we see across a CMIP ensemble pre-industrial case. And the parameters that yielded the largest temperature change are those related to soil hydrology and stomatal conductance. The other abiotic parameters we included that had a smaller global temperature impact were related to aerodynamic resistance, stability, and snow. And the other plant-related parameters that had a larger impact influenced photosynthesis, plant optical properties, temperature acclimation, biomass heat storage, and canopy evaporation. I wanted to call out this N-stem parameter in particular since biomass heat storage is a relatively newer addition to the model. And I think this coupled sensitivity experiment really emphasizes the importance of looking at the impact of land model developments in a coupled context, since we found that uncertainty associated with biomass heat storage parameterization could yield a 0.6 degree spread in global mean land temperature, while in offline sensitivity analysis of the addition of biomass heat storage, there was kind of a minimal influence on mean temperature, though of course a large influence on the diurnal temperature range. These parameters are all influencing temperature through slightly different land surface properties. And because albedo, evaporative resistance, and roughness are emergent rather than prescribed properties of CLM, by sampling these 18 parameters, we're creating a bunch of different combinations of changes in albedo and evaporative resistance and roughness. And for this subset of parameters, we found that the global scale land temperature changes are mostly driven by changes in evaporative fraction. And while these parameters are all modifying different aspects of the model, we found that there's a pretty consistent pattern of warming across our ensemble. So this pattern shown here is the leading mode of variance across our parameter perturbation ensemble, and it explains almost 80% of the variance in mean temperature changes across the parameter perturbation experiments. So when we're increasing or decreasing global mean temperature by perturbing these parameters, it's largely along this mode of temperature change. And when I first saw that leading mode across our ensemble explained so much of the variance, I thought that maybe perturbing these parameters is just kicking off your kind of classic Earth system climate feedbacks. But we see that the land-driven temperature changes are forming a really distinct spatial pattern from what we see due to radiatively driven warming. So land perturbations aren't just kicking off the same climate feedbacks we see in other cases. It's really kind of a unique signature. We also found that precipitation is also sensitive to land parameters. I'm just going to talk about global mean or annual mean precipitation changes. But one of the benefits of the length of our ensemble is that we can also look at things like interannual variability. In some parts of the globe across our ensemble, there's over a 20% change in annual mean precipitation. And some of the climatological hotspots of precipitation sensitivity to land parameters align with these shorter timescale hotspots of land-atmosphere coupling. So I want to emphasize that we're quantifying a very different metric. So instead of looking at daily to seasonal relationships between land processes and atmospheric state, we're looking at climatological changes. But some hotspots, such as the central United States and parts of the Middle East that pop up in more traditional metrics of short timescale land-atmosphere coupling, like from Coster et al., align with the same spatial pattern that we see. They're not entirely. And beyond just identifying where precipitation is most sensitive to land process uncertainty, we can also use this ensemble to probe the mechanisms through which land parameters can influence precipitation. So this figure is showing just one example of this. This is the leading mode of variability in annual mean precipitation across our ensemble, looking just at tropical land. This explains just under half of the variance across our ensemble. And it's characterized by this interesting zonal asymmetry, where there's an increase in precipitation over the maritime continent and tropical Africa, but then there's this interesting dipole pattern in South America, which includes a decrease in precipitation in the east. And this pattern closely resembles the asymmetric precipitation change that we see from plant physiological responses to CO2, which Gabe Cooperman quantified in his 2018 paper. So in CESM1, modeled plant responses to CO2 decrease evapotranspiration across all tropical forests, but that ET decrease drives opposite changes in precipitation due to differences in orography and the extent to which precipitation is coming from non-local moisture transport or precipitation recycling. And that mechanism aligns with how these different parameter perturbations relate to this mode of precipitation change. So parameters that make it harder to evaporate water, like reducing the maximum hydraulic conductance of plants, have a positive scaling along this mode, while parameters that make it easier to evaporate water, like the inverse of that at higher hydraulic conductance or a high Medlin intercept, they're driving the inverse of this pattern. And across the ensemble, there's this kind of robust relationship where this mode is negatively correlated with the magnitude of the change in tropical mean evapotranspiration. So even though these parameters are tuning different knobs in the land model, this suggests that they could be influencing precipitation through a consistent mechanism. So hopefully I've convinced you that land parameter uncertainty can significantly influence the mean climate state. There are a lot more examples of this, but just looking at the kind of annual mean to give a sense of what we could do with this ensemble. There are a few implications for this. So first, it means that we need to account for land parameter contributions to both uncertainty and biases in model representations of present-day climate. So I think this is a challenge for this community to think about, is how can we analyze if new behaviors in CLM will have a coupled impact, and how can we identify this early in the model development process so we really know when CLM is going to change the mean climate state, potentially improve the mean climate state, but something we need to think about. This also means that if land parameters change over time, I think this is especially possible for some of the plant traits, which are static parameters in the CLM framework. If those parameters can evolve over time, that could generate atmospheric responses. And broadly, land-driven climate changes are not going to look like radiatively driven climate changes. I just showed this through the spatial pattern of temperature change due to radiatively driven versus land-driven temperature change. But this is kind of a consistent takeaway that we see when looking at patterns of precipitation change and other metrics as well. So with that, I'm happy to answer any questions. Thanks.
Okay, questions for Claire?
Oh, yeah. We're just wondering if you compared with Katie and Daniel's sensitivities and if you find any big differences when you couple.
Yeah. So I used their analysis to select the parameters. And for the most part, there's kind of consistent scaling where even though temperature changes in the offline model are very, very small, the kind of relative ranking holds when looking in a coupled context, largely, not always true. The one exception to that is the zeta max stable parameter in the offline case has a really big influence on turbulent heat fluxes and temperature, and has a really muted response in the coupled case. But other than that exception, the ranking is pretty consistent.
Is there a question online?
It's a little hard to hear your questions in the room. I don't know what was said.
Okay,
I don't know if people
maybe
can
the
speak
room
up.
mics weren't on? Yeah, he's giving me the
Okay.
So
I can repeat the question.
It was the room mics,
Okay.
yeah. But yeah, Isla's question was about the ranking across the uncoupled versus the coupled ensemble. So yeah, go ahead.
For the precipitation variability, is there a role of large-scale circulation changes in response to land parameter changes, or is it mostly the evapotranspiration, like local versus, say, dynamic or
Oh,
remote?
great question. Yeah, that's something I definitely want to dive into more. There definitely are some global scale circulation changes. So for example, the second mode in the tropics looks a lot like the ITCZ moving in response to changes in like the hemispheric asymmetry from there being more land in the northern hemisphere. I haven't dug into that mode in as much detail, but I think, yeah, there's definitely a signature of some global scale circulation changes.
Yeah, one more, go ahead.
So when you were doing the perturbation of the plant-related parameters, were you doing them in concert across all the PFTs?
Oh, great question. Yeah, so I was using the same setup as the CLM5 PPE. So I was changing all the PFTs at once, but not necessarily by the same amount. So to the extent possible, the community developed parameter ranges were observationally informed. So sometimes there was a larger range for one PFT than another, but we were going to the minimum and maximum values at the same time for different PFTs.
Cool, thanks so much, Claire. Thanks. We'll move on to our next talk in this session. So our next presenter is Thomas Kaboo, presenting on scaling up and point scale calibration using neon data, improve coupled carbon water cycle and CLM at a regional scale. And you're going to just make sure you switch it. Turn it on. Perfect.
Okay, hey everyone and welcome. I'll be giving a talk on scaling up, and the question I'm asking today is, can point scale calibration affect or improve simulations in CLM at regional scale? I want to pass my acknowledgement to my supervisor, Dr. Sajiv Kumar. Dr. Daniel Kennedy has been very helpful, Dr. Will Wida, and the Land Model Working Group. They have been so helpful in helping me come up with my methodology and also with this particular analysis. So a lot has been said about model uncertainties, and our key focus in our research, we are looking at two things, ET and GPP. And for one, the first thing that we are looking at is this methodology helpful in improving the model performance in simulating these particular variables at point scale? And then once we are certain about that, then we can now be able to proceed and apply that at regional scale. And this particular graph is just giving us a slight overview of how the model simulates ET, and you can see there is a negative bias, like it underestimates ET, that particular site that is a tall neon site. Some of the progress in addressing uncertainty has been use of high resolution forcing data sets, model calibration and parameterization, and use of AI and machine learning. And we all come to agree that global calibration is a challenge based on the fact that CLM is a very complex tool and it requires a lot of model parameters, and it's very complex with so many parameters, and it makes calibration very difficult. And on the other hand, point scale simulations, they are easy, less computer intensive, and these ones you can run several of them within a very short period of time, and even spinning them up to bring it to equilibrium, the carbon sinks and all the other processes, it's very easy. So we're looking at, there have been approaches whereby some research, they only look at carbon cycle calibration. They only look at those parameters in that particular aspect. Others look at the water cycle calibration, like just using the same technique in hydrological calibration. But in our research, we are trying to look at parameters from all these aspects, like from hydrology, from latent and sensible heat fluxes, and also from the vegetation type. Data and methods. One appreciation is the neon data sets, and neon data is a new resource that can be utilized to constrain land surface model parameters. And the CLM neon tool has enabled use of neon data sets to test various hypotheses. Our research, we're only focusing on using the neon data sets, and we're looking at those particular three ecoregions, that is domain 8, domain 7, and domain 3, and only looking at the OSBS site, toll site, and ORNL sites. And this is the framework of our methodology. We are applying the framework that has already been designed, and just to give you a brief overview of what we are doing, we are getting the CLM parameter file, the default parameter file, and sorry about that. And we use Latin hypercube sampling, and we have selected about 30 parameter sets with maximum and minimum values, and we perturb those parameters within that space to generate about 400 parameter files, and we run the default simulation. That is 200 years of spin up, 4 years of production run. Then after that, we clone that, and we use each particular parameter file, we spin it up, and then also do a production run for each. And that we do an analysis using 3 performance metrics. We're using the mean bias, RMSE, and R squared to identify the best performing simulations. And then we also did a parameter sensitivity analysis to identify the most sensitive parameters. For the parameter sensitivity analysis, we used a methodology which was proposed by Sheikh Loskem in 2021. I'm sorry if I didn't pronounce that well. And he introduces a new tool of using a variance-based sensitivity analysis that it recycles the existing data. That is, for our case, we have 400 simulations, 30 parameter files to determine parameter sensitivity. So how we looked at our results is the first diagram is showing us a single parameter file. And what we did, we identified the 10% best performing parameters, and we mapped that out based on the single parameter maximum and minimum values. And we also mapped the default parameter value and also the best performing parameter. And on the ET and GPP simulation, we also mapped the top 10 best performing parameters, the default simulation, the observational data, and the best performing parameter file. So this particular figure might look very complicated with a lot of figures and a lot of presentations. What we are doing, we are presenting for the 3 sites how the top 10 best performing parameters are varying within each particular site and comparing across each particular site. And I just want us to look at some few parameters. This one is a mistake. It should be pointing to the end stem. So these particular highlighted parameters, we see that optimized parameters can be considerably different. And when you look at the default parameter, for example, for the fraction soil, saturated soil, where the DSLR initiates, you can see like the default parameters are on the lower side, almost 0. But the best top 10% and also the best performing, the best simulation and the top 10, they are all very different from the default value. And this is evidence. Also, when you look at the D-leaf, it's also giving us a similar explanation. And with the PSI, for me, it was very interesting in that it's shifting from the positive side, and all of a sudden, the top 10 best simulations, and also the best simulation, they are all on the negative side. And this is how the model performed after we extracted those best 10 best performing parameters, the default. You can see the red line, which is showing the default simulation. The black line is showing the observation, and the blue one is showing the best simulation. And yes, our parameter optimization improves the model performance. We see a significant correlation, as we see a significant improvement in the model in that the best simulation is trying to match the observation. And one of the challenges we had with especially the ORNL site as compared to the other 2 sites is the data gaps. In the ORNL, they don't have consistent data from 2018 to 2021. So we sort of like felt the analysis might have been better, or it would have helped us to identify the distributions better if we had like a good data set, because it also helps, or it also affects the performance matrix evaluation, like if you are using just 2 years of data as compared to when you are using 4 years of data. For the sensitivity, once we applied the model, we grouped our parameters into 3 groups: the hydrology-related parameters, vegetation related, that is photosynthesis, stomatoconductance, and also we had the sensible and latent heat fluxes. That is, the blue is vegetation-related parameters, blue is the hydrology-related parameters, green is vegetation and sensible heat. And we see, for example, for the latent heat fluxes, the Jmax B1, SLA top, that is the specific leaf area at the top of the canopy, the leak canopy scalar storage, and the Medlin intercept, and the WC to WJBO. They are some of the most influential parameters to this particular variable. And again, when we look at the GPP, we see the parameters that are vegetation related, they are more like affecting it, which for me was not a big surprise because GPP, yeah, you expect some of those parameters to be there and having a large and significant impact on GPP. And now looking at all the three sites, how do the parameters compare from site to site? So on the top panel, we are looking at the latent heat fluxes. The first site is the ORNL site, we have the OSPS site, and we have the toll site. And the results are very consistent we see like almost the most influential parameters, they are consistent across the sites. For me, I would say like I was a bit surprised because I expect different sites, they have different dynamics, and maybe I was looking forward to having different parameters influencing these particular variables, but yeah, like they are very consistent across the three sites. So I'm still working on it. Like now I'm looking forward to applying the best parameter file to run a regional simulation and look at the result and see like if we can now prove or test our hypothesis that is this point scale able to improve the regional scale, because it shows that it can improve at point scale. Thank you, and I'll be happy to take questions.
Questions for Thomas? Daniel, go ahead.
Hi, Thomas. Yeah, that's a great talk, and I think your question is fantastic. The question of how do we leverage point scale and will it work regionally? I had a question about like BEST. You have 3 sites and 2 variables, but presumably your regional simulation is going to require like 1 parameter set. How are you going to decide what's best among all of the different parameter sets if there are like, conflicts in optimizing GPP versus ET, for example?
Yeah, okay, thank you so much. But when I go back to the seminar and how you presented, like we've seen from the seminar that, for example, if we look at simulation, maybe 100, it gives maybe the best for ET, that is at toll site. And when you go to OSPS site, you find maybe the parameter file at 209 was the best. So in this case, we are looking at each site, we have selected the best performing parameter, and now we are going to run like 3 different simulations using each best parameter set from each site. And we're also going to compare that and look at the values and how they vary.
Cool.
Question, yeah, there's a hand raised online. Go ahead, Heidi.
Oh, I mean, one of the reasons why we go for parameter calibration at point sites is because we have a lot of data there. And once you go to regional scale, you're going to have a big lack of data, I guess, for comparison. So how are you going to assess the performance of your regional runs?
Okay, that is one thing that we've been looking at, and we have a number of options because there are reference data sets that are already in existence. Like, for example, we have the ILAM package. So one of the things that we are looking forward is to compare, for example, our ET and GPP from the regional run and how the ILAM package gives the result. So that's one of the data sets that we are going to look and maybe benchmark our model performance.
Cool. Thanks so much, Thomas. I think we should move on to our next presentation. So our next presentation is by Montesir Maruth, who is in the room. Yes, okay. Let's start.
So good afternoon, everyone. I'm Muntasim Maruf, PhD student at Auburn University. Today, I'm going to present a glimpse of our work titled Neon Testbed for High Resolution Climate Assessment. I'm really grateful to my advisor, Dr. Sanjeev Kumar, also Dr. Keith Oleson, Dr. Nagin Sobhani, and the whole land model working group. Without their help, I cannot develop these models and conduct this work. So this is the outline that I will talk about today. So our general hypothesis was high resolution model improves the water cycle predictability. And to test the hypothesis, we have developed 2 high resolution model and 1 low resolution model. And we have compared our developed model with the reference grid dataset, which includes ERA5, MIRA2, LERI, GLEAM, and SMERCH. So the result shows that CLM high resolution improves the performance, but it is not very significant. And also it depends on the reference dataset. And it reduces the soil moisture variability and increase the soil moisture residence time, which is impacting the water cycle predictability. Here is a few literature review about our work. So looking into the literature, we found that a study has been conducted where the authors developed CSM 1.3 high resolution and low resolution model, and they compared global mean temperature, sea surface temperature, and extreme events. So they found that the high resolution model performs for SST and extreme precipitation. But in most of the cases, high and low resolution model, they are kind of similar and consistent. Also in another study, they compared high resolution and low resolution model of CLM4 for sensible heat flux and soil moisture. So they found that normalized root mean square has been reduced for sensible heat flux and soil moisture. So here is the model we have developed. We have developed CLM high resolution and NOAA-MP, and the spatial resolution of our high resolution model is 12.5 kilometer. And we have developed one low resolution model. The resolution of that model is 100 kilometer. So both all the model used NL-DAS2 forcing, and the temporal resolution of our model is 1980 to 2018. This is the list of the data sets, reference data set we have used. So we used ERA5 and MIRA2 for latent heat flux, sensible heat flux, and soil moisture comparison, LERI and NEON for latent heat flux comparison, and SMERCH and GLEAM for soil moisture comparison, and WIG for runoff comparison. So to compare the data sets, we have used some of the statistical methods. We applied bias, normalized root mean square error, and we have used tailored diagram to visualize the difference between the data sets. So in short, I took this picture of the tailored diagram from the NCL website. So if I want to explain this a little bit, so the tailored in the x and y axis of the tailored diagram, there is normalized standard deviation, and the radial axis is the correlation. So for instance, if I want to find the round red dot, which is indicated by 2, the correlation of that would be, so we have to draw a line from the 0 and extend it until the radial axis. So if we extend the line from 0 to the radial axis, we'll find the correlation around 0.7. And the standard deviation of that point would be 0.5. So this is the ETA, normalized root mean square error comparison between the models. So the first row is the CLM high comparison with ERA5, MIRA, and LERI. And the second row is the NOAA compares with the reference dataset. And the third row compares the CLM low with the reference dataset. And these numbers are like the average normalized root mean square error across the area. And we see that it varies between the reference dataset. For instance, if we see the ERA5, the CLM high resolution, NRMSE of CLM high resolution is 5.4, NOAA is 6.6, and it reduced in CLM low to 4.8%. And if we see the MIRA ones, we see that the low resolution model of the NRMSE is 7.5, NOAA is 7.5%, and which is reduced to 7.2%. And in the LERI, it also increased, the NRMSE has increased in CLM high resolution model than the low resolution model. So here's the Taylor plot for the MIRA. We compared our data set with the MIRA one. And to get a better view, we have reduced the X and Y axis to 2. So some of the ecoregions has cut off. So these, these points represents the weighted average of each ecoregion. So here we see some of the ecoregion has improved in CLM high resolution. For instance, if we see the region number 3, OSBS, we can see which is the plus sign. The normalized root mean square error is 0.45, and which has which is 0.33 to the when is CLM low resolution. And if we see the TAL site, which is the triangle symbol, the normalized root mean square is 0.6, and in low resolution, which is 0.42. Sorry, this is the correlation ones. And for the California, Southern California, which is 17 SJR, the correlation has reduced to 0.96 to 0.93 from high resolution to low resolution. So here we see some of the regions shows the significant correlation improvement, and some of the regions shows like not a very significant. And finally, this is all the regions average, the star symbol. Here we also see the correlation has improved, also the normalized standard deviation. So this is the daily soil moisture time series. Here we see that the black one is the ERA5, the blue one is the CLM high, and the red one is the CLM low resolution. So here we see that CLM low resolution shows faster soil moisture decay than the CLM high resolution. And we see that CLM high resolution root mean square error is 0.028, and which is increased in CLM low resolution to 0.048. So we also did the variability difference between CLM high and low resolution. Here we see that the average difference between the high resolution and low resolution is minus 0.168%. And this is the soil moisture residence time. Here we see that in the high resolution, both in NOAA-MP and CLM high resolution, the SMRT has been increased. And CLM high resolution is very consistent with the ERA5. Though NOAA-MP shows a little bit inconsistency, but overall the high resolution model shows, both models shows the higher SMRT than the low resolution model, especially if we see the Southern California and Mississippi River Basin, it shows the higher SMRT. So in summary, we have done like a lot of extensive comparison, but due to the time limitation, we only showing the ET and the soil moisture comparison here. We also did sensible heat flux and runoff comparison with the reference dataset. So in summary, we can say that improvement of the high resolution is not very significant. The high resolution model improves, but it depends on the reference dataset, and it varies between regions to regions. So in some regions, the performance of ET and soil moisture has improved, and in some regions, the low resolution performs well in terms of ET and soil moisture. But the high resolution model reduces the soil moisture variability, and it has increased the soil moisture residence time, which is impacting the better water cycle predictability. So yeah, that's all from me. Thank you.
In the room or online? I did have a question about, kind of your first point there, that the improvement of high resolution is not very significant. How much do you think that's related to the resolution of the data sets that you were using? So you have that table that showed, I think, the different sources of the data, and they seem to be varying quite a bit in terms of their resolution.
The reference data set?
Mm-hmm. Yeah.
So there are different resolution, but we regraded.
Mm-hmm.
When we did the analysis, we regrade the reference data set and made it to the same resolution.
Mm-hmm. Yeah, I'm just wondering if that might impact some of the assessment across different variables.
Yeah, it might be.
Yeah, okay. Yeah, go ahead, Ben.
Yeah, thanks. That was a great talk. The soil moisture residence time, that's a really interesting result. Is there a mechanistic hypothesis underlying that difference?
It might be, it has increased especially in the irrigated regions. So irrigation might be the reason. So, in high resolution, it might capture better the irrigated regions. So that's why the SMRT has increased in those regions.
Great.
Any other questions? Okay, thanks so much. Yeah, I think we'll move on to our next talk, which is by Tegan King. So this is going to be talking about PRISM precipitation, a new neon CTSM data stream.
Okay. All right, can you hear me okay? Awesome. All right, well, thank you. I'm Tegan King. I'm an associate scientist in the Climate and Global Dynamics Lab, and I'm going to be chatting with you all today about using PRISM precipitation in our single point neon CTSM runs. I also wanted to thank all of the collaborators that have been working on this and everyone who's been on the neon NCAR collaboration as well. Everyone has been very, very helpful for this project. So I'm going to start out sharing a little bit about some background motivation for why we want to be introducing this new DATM stream, and then I'll talk a little bit about some of the preliminary results that I've found, and then share a bit about the workflow that I was using as well. So some general motivation for the NEON project, which maybe we've touched on already a little bit, but that's to facilitate parameter calibration and uncertainty quantification. We also have a number of folks in the terrestrial sciences teams that are working on advancing ecological theory at the macro scale, and there's a lot of various projects that are contributing to this effort. We're also working to develop ties with the Earth system prediction studies and to integrate new observations into model calibration, evaluation, and validation workflows. So this here is an image of one of the NEON data sites. So there's a lot of different data that is collected at these sites. The image on the right shows one of the primary sites that collects precipitation data in that double-fenced area there. And NEON has these tipping buckets. The top left is an image of a tipping bucket that's not exactly from a NEON site, but we found a picture of a tipping bucket elsewhere. And then we have these throughput or through-fall collectors that are sort of redundant data streams that we have at the forested sites for NEON. And so we end up having some data that gets recorded when there's, for instance, like wind or other features that could affect the gauges that we have. There's sort of a spring mechanism that gets somewhat easily triggered by that. And so having these additional redundant data streams at our forested sites is really useful. And at the same time, there have been a lot of data calibration challenges in dealing with wind factors or other things that could cause noise in our precipitation data. So at the grassland sites, we don't currently have that redundant data stream, and so we are trying to figure out a way to improve our current precipitation data that we're using at the NEON sites. So some more motivation for using this PRISM precipitation came from actually looking in particular at the Moab site. I was just looking at some different data for that and noticed that we had some unexpectedly low GPP at this site. And so in digging into that a little bit more, I was looking at precipitation as one factor that could influence GPP and noticed that as you can see here, in early 2018, we have pretty low precipitation from the NEON data. And so I was comparing that with, in purple, you can see the PRISM precipitation data, which shows a number of events that were not quite captured by the NEON precipitation data. So I wanted to see if other sites were acting similarly, and I put one example of the tree site, and you can see the PRISM precipitation is in blue on the plot on the right, and the NEON precipitation is in orange. And in 2019, there were sort of some gaps that the precipitation events weren't really captured by the NEON data, but they were captured by the PRISM data, even if other time or areas on that plot for different times looked a little bit more accurate. So we wanted to kind of find a way to use this PRISM data as a potential additional precipitation input and to really address some of those gaps that we were seeing with the NEON data. So I wanted to look into this just a little bit more and looked at some of the cumulative precipitation over the course of a year and try to determine whether or not the PRISM precipitation was actually better. And so I want to note that this is very year-specific and site-specific. For these plots, I particularly showed the Jornada site in New Mexico in 2018 in the top plot, and then in 2020 in the bottom plot. You can see that in 2018, the NEON precipitation in yellow kind of misses a number of events in the latter part of the year, whereas in 2020, it does a significantly better job. And then you can also look at the PRISM precipitation is in red here, and the blue lines are some sort of ground-based data that we got from Allison, who provided the SCAN and NOAA ground-based data sets that we're using sort of as a benchmark. So you can see that the red lines from the PRISM precipitation data are a little bit closer to the blue lines in general and are perhaps a little bit of an overestimate, but that they tend to be a lot closer to what we expect the precipitation data to look like. So overall, the PRISM data seems a little bit closer to the ground-based data and oftentimes captures events that the NEON data seems to potentially miss. And another really nice feature about the PRISM data is that it doesn't have some of the gaps that we have in the NEON data. So that makes it a lot easier to work with when we're using it, ingesting it into CTSM. So I wanted to go ahead and actually try implementing this PRISM precipitation data in the DATM streams, and I wanted to look at what some of the preliminary output is. So I took a look at the latent heat flux biases, and this slide compares the latent heat flux biases with the NEON precipitation data as input to CTSM, and then with the PRISM precipitation data as input to the CTSM runs at each of these single point sites. There are differences between these two plots. You can take a look at some of the details here. I'll point a few out though. In North Dakota, for instance, we see the plot on the more eastern side of North Dakota does have a stronger bias with the PRISM precipitation data, and that's one that I was kind of looking at and wanted to, I guess, be a little bit wary of. But a number of other sites have a slightly less strong bias with the PRISM precipitation data. If you look, for instance, at the sites in eastern Tennessee, that those are a little bit lighter colored. Maybe a number of the sites have a slightly more positive bias with the PRISM precipitation data, but there does seem to be a little bit of progress towards a less biased overall. I also want to point out the Teak site in California shows a slightly less strong bias with the PRISM precipitation data, as well as the Jornada site in New Mexico, and we'll take a look at those two in a little bit more detail in the next slide. And I, once again, want to note that this is very site-specific. So we wanted to be able to use some climatologies to provide more site-specific insights on what we were seeing in the previous plot. So here, I'm sorry, the font is a little bit small, but if we look at the left side is plots for the Teak site in California, and the right side is for Jorn, which is in New Mexico. And then the top tier of the plot is net radiation, and then the next tier is the sensible heat flux and the latent heat flux. And as far as the color scheme goes, we're looking at the blue is CTSM run with the neon precipitation input, and the red is CTSM run with the prism precipitation input. And then the yellow is kind of what we're comparing those to as like a benchmark. So if we look at the plots on the left for Teak, the site in California, we can see that the output is more similar to the expected observations when we're using the prism precipitation data as an input data stream. And that is pretty consistent throughout the whole year here. And then for Jorn, it's also showing that our prism input precipitation data is generally acting as closer to the observations. But if you look, for instance, specifically at March or April, the latent heat flux for using the prism input precipitation data is perhaps like a little bit closer. And in general, I just wanted to point out that there are some situations where the neon precipitation data is still helpful to look at, and someone may want to compare what their site looks like with the neon or prism precipitation data. And then really quickly, just to provide some insight into what implementing this prism precipitation data actually entailed, I was working on taking the prism data from their website and kind of converting it to the correct conventions for ingestion into CTSM, and then including those prism precipitation data in the DATM streams. And then I updated some of the user mod directories to include the new DATM streams and modified some of our shell commands to fix previous site-specific data gaps that we had been addressing. And then I was using the run neon script, which is a very helpful tool to be able to spin up with the AD and post-AD runs and then see what the transient cases looks like. And then I also have some additional resources if anybody is interested. I put together a Jupyter notebook that kind of is an easy way to compare some of the prism and neon precipitation output. And we also will have a paper that Donica is leading that is coming out or that is being submitted to GMD probably this week or next week. So that may be useful to keep an eye out for. And with that, I am happy to take any questions that anyone has.
For Tegan? Yeah, go ahead, Lily.
Hi, Tegan. Great presentation. It's nice to see this operational. I'm wondering how much of the bias is due to snow versus rain in the precipitation data. You highlighted Teak, which is a Southern California site that gets a lot of snow. Tipping buckets aren't particularly good at capturing snow. Do some of the neon sites have pluvios or other like ways of capturing snowpack? And how much does that potentially influence the poor neon precipitation data?
That's a really good question. So that was something that I was actually kind of looking at. I started out looking at the Moab site in particular, and it looked like snow was not really a really large factor there, and we were kind of seeing the same thing, but maybe that would be something to look into in more detail at some of the other sites as well. Yeah, thanks for that question.
Can I just add a little bit? So this goes back to the neon core design, but like the core site in each domain has those big fences, like the double whatever, I can't remember what they're called, with the drifter inside. So those are really good at snow, like kind of, but not at windy places like Niwot. But that's because of the wind, not because of this sensor itself. Other sites, and I can't remember. I don't think Teak is a core site. Those are the ones with the tipping buckets, and you're totally right. Those are terrible for snow. So it's a challenge, but it's like really site specific, and so it kind of takes, I guess, a user who knows something about their site to really dig into it. So we're trying to provide the tools, but not too much judgment about the quality of the data that we're getting that's not our own.
Let's go to Sanjeev's question, then we'll go to Phil. Go ahead, Sanjeev.
Yeah, this is great presentation. I was wondering, given the neon or point-specific data, like Prism is a graded data, that's why it's kind of continuous and useful. Given that neon is only kind of limited number of the station, are you also thinking to having a provision to incorporate the nearby NOVA station data into the data stream, and that will make the data more valuable for the point scale experiment?
I'm sorry, I didn't quite catch what the additional data set that you were referring to was.
The NOVA station, NOAA.
Okay.
I think Dave Durden looked into that, and he was dubious that it was any better. And it kind of suffered from similar gap in data quality issues.
Okay.
But it's something we talked about with Dave.
We did also do some additional comparisons with other data sets that had more gaps, and that was one of the really, really nice features about Prism, is that it's pretty continuous.
Thank you.
It seems like you've done some really good analysis here to show the kind of improvement from Prism. I'm curious if you have kind of brought this back to the NEON team to like have them produce like derived precipitation product, and if they've had any responses to that.
Yeah, so I think that the NEON team is currently working on updating some of their algorithms that will be released, and they're gonna kind of release data from the past with like updated calibrations in 2024. So I think that that is something that is gonna be a big improvement on the NEON side of things. And we have been in collaboration with them and talking with them about this project. So I think that's one update that is gonna be happening in the future. But we also kind of want to be able to implement a way of introducing new data streams that I think this is kind of a helpful example of how to make that happen. So there's kind of options for the user to decide if they're interested in potentially updated NEON precipitation data in the future, or looking at the Prism data.
Thanks.
And then before we go to Dave, Donica had a comment in the chat related to the previous question about NOAA sites being a little far away from the NEON sites, so just another factor to consider. Go ahead, Dave.
You guys, maybe I already asked this once before, but presumably this must be a problem at all tower sites, not just the NEON tower sites. And so I'm curious if you guys have looked at, what do they do at the Ameriflex sites? What do they do at other standard tower sites? Are they using a similar protocol or different, or is this maybe still a problem in a lot of those sites?
Yeah, I'm not totally sure. Will, do you have information?
I only know at Niwot, and it's a total mess. Like there's pillows that you can use to get snow. There's SnowTel and CRNS that you can get snow data from. There's at least 2 precipitation gauges. Some of those are included with the Ameriflex, some of them aren't. So at least, I think the real challenge here is that the data are so messy, like the obs are so messy, especially for precip, that I think what's really nice about about the work that Tegan's done is that it provides an avenue for people to add their own measurements if they think that they're better for some reason. And Prism is just a standard way of doing that.
Yeah, I agree, it's totally nice, but maybe it's just worth looking at the one, I think OneFlex, right, has been they've taken all the data and massaged it and made sure it's usable by people and see if they had what their strategy was.
I'd be shocked if they had anything
They
better.
use ERA, which is not gonna be better.
Right.
Okay, so they just, okay.
Joshua, go ahead.
I can't speak for all meteorologists, but at our towers, we always just go straight to the nearest airport. That seems to be the first approach for most people, but I don't know that that's the standard or the final thing, but it's that's probably what the Prism is based on, is that network, and so you're basically just not using interpolated data, you're using the data that probably generated Prism for that. But sometimes you don't have an airport nearby, so it's not great.
And then there was a comment, can you bring up the chat again? There was a comment from Sean Burns that I just wanted to make sure we saw. At Niwot, we make use of the nearby NOAA USRN site. Okay. Cool, thanks Sean, thanks everybody for the questions. I think we should move on. Our next presentation, we're gonna switch to remote. Katya J is online, so let's see, I got it. I'm gonna stop sharing the screen so she can share her screen. How do I move on to the other screen?
Can you see my slides?
Yes, we can see your slides and we can hear you. So thanks,
Great.
Katya. Go ahead.
All right. Hi, everyone. I'm Katya. I'm a postdoc at CU and visiting at NCAR, working with Will. I was bummed to not be able to join you all in person today, but unfortunately, I'm stuck at home with COVID this week. But I'm excited to be sharing my work using CLM with the hill slope hydrology configuration to do some point scale simulations across an alpine tundra hill slope gradient. And I also just wanted to quickly acknowledge all of my co-authors who've contributed to this work, as well as our funding sources. So our site of interest is Niwot Ridge, which is a long-term ecological research site, which has tons of measurements going back to the 1980s when it was established as an LTER, as well as a number of newer exciting data sources, such as the flux towers that have been running since 2007. You can see one of them here. And this is a high alpine environment, so it has a lot of microscale variation across the landscape due to differences in topography and wind and snow redistribution across the landscape. And similar to other alpine sites across the world, this area is undergoing pretty rapid warming. So you can see in this plot in the top right, this is showing the climate record going back to 1950 at an alpine and subalpine site at Niwot, and you can see that warming trend over the past 70-ish years. So in terms of thinking about changes across a topographically complex landscape, such as the alpine tundra, the hill slope hydrology configuration in CLM is a really great tool for addressing these kinds of questions. As Iris mentioned yesterday in her talk, we can have multiple columns within a grid cell that are connected to each other with downslope lateral flow. So that allows us to have hydrologic connectivity. And we can also think about the effects of aspect, which I'll talk more about soon. And in this picture here, you can see kind of our representative hill slope at Niwot, which I'll be referring to with this cartoon throughout the talk. And it basically has an east and a west facing knoll with a lowland area in the middle. And you can see in the background here where there's still snow, and this photo was taken in late June because of that east facing exposure and wind. That's the area that we'll be referring to as the moist meadow, in contrast to the foreground where you can see really dry, rocky soils with less productive vegetation. And this is a really windblown area. It doesn't accumulate much snow, known as the dry meadow. And then in the lowland area in between, we have the wet meadow, which tends to have lots of water subsidies from upslope and more shrubs and more productive vegetation. And we also tend to see kind of a gradient in plant traits along the spectrum of moisture. So the wetter sites tend to have more resource acquisitive plants, in contrast to the drier sites that tend to have plants with more conservative growth strategies. So we wanted to see if we could use CLM with hill slope hydrology to reproduce observed patterns across this topographically complex landscape in terms of snow and soils and productivity. And then also thinking about if we can do that, how can we then look across different aspects and see how these patterns change over the landscape? And then lastly, thinking about landscape position via aspect and the different vegetation communities I just described, do those factors moderate exposure to future climate change? So I'm just going to give you a really quick overview of our model setup. We had to make it to better fit this alpine site, and we're using input data from 2008 to 2021. As I mentioned, there's a lot of data streams available at Niwot, as well as some Ameriflux radiation data that we're using as inputs. And then we also created 3 different parameterizations of Arctic C3 grass in order to represent these 3 different communities. And to do that, I used foliar trait data that we have from Niwot, as well as phenology traits that I pulled from the PhenoCam network up there. And we also made some changes to things like plant hydraulics to try to better represent the different growth strategies in these communities. And then again, we have a ton of observational data sets available to validate our model results against. So things like snow depth, soil temperature, soil moisture. I'm just going to show one figure from that. And in the interest of time, I want to focus more on the aspect results today. But just to show you some model validation really quickly, in this figure, we have our observations in black and the model results in colors, with the moist, wet, and dry being green, blue, and orange. And these results are averaged over the time series by day of year to show you kind of the annual climatology. And on the top, I'm showing snow depth, in the middle, soil temperature, and on the bottom, soil moisture. And you can see that the model is doing a pretty good job of capturing these patterns across the landscape. And we see that gradient in snow, as I mentioned, with the moist meadow having the deepest snowpack due to the changes that we made to the precipitation scheme. And then that translates into differences in soil temperature and moisture as well, particularly with the more snow-covered areas having warmer soils during the winter. So hopefully I've convinced you that the model is doing a decent job at this site. And now we want to focus on changes with aspect, which we know is really important in the Alpine. So we put all three communities on a north-facing aspect and a south-facing aspect with the same slope and ran similar simulations. And then we also used anomaly forcing to project out to 2100. I'm just going to show some of the aspect results first. And here we have snow depth on the top and runoff on the bottom, with the dashed lines being the south aspect, and again, averaged over the time series by day of year. And as you'd expect, we found that there was less snow in the south aspect, although surprisingly, the date of snowmelt when there was no more snow was actually the same in all three communities between north and south, which was a little unexpected. But I did find that there was an increase in the growing season overall on south aspects of around 7 to 10 days, depending on the community, likely due to differences in soil moisture and temperature that I'll show in a minute here. And then on the bottom, you can see the altered runoff, so altered timing of runoff and decreased runoff, particularly here in the wet meadow, where that peak is happening about 2 weeks earlier in the year. And now looking at soil temperature and moisture, again in the south and north aspects. As you'd expect, the south aspects were both drier and warmer. There was some interesting kind of seasonal variation throughout the year of when those differences were occurring. So for example, in the dry meadow, we saw that soils were colder in the winter, and there was kind of a bigger difference in the winter than early in the growing season, in comparison to the moist meadow, where the north and south aspects were very similar throughout the winter, and then saw bigger differences in the summer, which suggests that there are some buffering impacts of the snow, which could moderate how these communities may experience warming in the future. And I also thought the pattern in soil moisture was kind of interesting here in the wet meadow, where north and south aspects were really similar early in the growing season, and then the south aspect dried out a lot more throughout the growing season, likely because of that earlier peak in runoff. And now I'm going to focus in on those snow depth and runoff metrics that I just showed you, but only looking at the wet meadow. So here we have south aspect on the left and north aspect on the right, with the black lines representing the future scenario versus the blue lines being the control. And again, we're seeing altered timing of both snowmelt and runoff in this case. So the snow melted out about 2 weeks earlier in both the south and the north. And we also see just a decreased snowpack in general, especially in the south aspect. And then I thought the timing of the runoff peaks was interesting, where you see that it's a bigger difference here in the south aspect. It was about 25 days earlier, and that peak was actually slightly higher in the future scenario compared to the control, suggesting kind of a large pulse event right after snowmelt in comparison to here in the north, where the peak was smaller in the future. But these shifts in the timing of snowmelt and runoff could kind of decouple the timing of resource availability and plant demand during the growing season, which could lead to increases in water stress and potentially shifts in plant composition and productivity. And then lastly, I wanted to show some metrics of changes between the control and future scenarios, looking by community and aspect. So in these plots, you'll see the boxes with the dashed lines are for south aspects and the solid lines are north aspects. And here I'm showing the change in mean annual soil temperature at the surface. And then in the dashed line at 3.5, that's the air temperature increase over that same time period. So we saw that the dry meadow was really tracking that air temperature change, in contrast to the snow-covered areas, which, as you might expect, were more buffered by that snowpack. So it's really cool to see that difference. And then here looking at percent change in growing season soil moisture. So this is normalized to their baseline values since they're so different. But we see that these changes were driven kind of both by aspect and community. In particular, the dry and moist meadow south aspects were the ones that dried out the most, in contrast with the wet meadow, where we saw very little difference between aspects and in terms of the soil moisture in the future, suggesting that those upslope moisture subsidies could potentially help kind of maintain similar moisture conditions in this lowland area. And then we also saw that the increases in growing season length were strongly moderated by aspect across all three communities. And in particular, there were larger increases in the length of the growing season in the moist and wet meadows, which makes sense since there were some large declines in the snowmelt date, as I showed before. And we know that growing season length is a really important control on productivity, especially in these alpine regions that have short growing seasons. So these kinds of shifts in the growing season can have cascading impacts on microbial communities and nutrient cycling. But overall, I think these findings show the buffering role of topography and microscale variation in the alpine, where rates of change will vary across this landscape based on these different microclimatic conditions. Lastly, I'm not going to read my conclusions just because I think I'm running low on time, but I did want to mention some next steps for this work. I've recently joined a team working on a growing convergence research project through NSF, where I'm going to be working on applying this similar modeling framework at some lower elevation sites. We have kind of an elevation transect going from a Niwot forest site down to Gordon Gulch and Tasso. We're hoping to use a similar approach with hill slope hydrology and hopefully using fates as well to co-develop estimates of climate refugia, which will be informed by stakeholder and land management needs. So I'm really excited to be applying this framework across the Front Range. And with that, thank you for listening.
Questions for Katya? Katya, can you talk a bit more about what you mean by climate refugia?
Yeah, for this new project, you mean? Yeah, so just the idea that certain areas of the landscape will be more buffered than others, kind of like what I've been talking about here in the Alpine, where certain sites are buffered by having more snow and more moisture. So in the future, as things are warming, certain areas may be able to persist with more similar conditions than others. And I think the idea being too that those refugia will shift in the future, but the project will kind of seek to use stakeholder perceptions and public perceptions of refugia and what they want out of those, and also use the modeling framework to kind of identify where those refugia might be located.
Cool, thanks. Okay, we're actually at time, so I guess we'll move on. Thanks, Katya. I hope you feel better. Our final talk in this session is by Linnea Hawkins. And let's get your... Okay.
Is my mic okay?
It does say that it's sharing.
If you just click the wrong screen when you share it.
It has to be on the same desktop. Just
Oh, it
go
does.
So Chrome is in full screen mode right now. If you take it out of full screen mode first, then you'll be able to put it on the same desktop.
Thank you. There we go.
Okay, let me move it back to you.
Thank you.
Right? Can somebody in companion mode let me know?
Yeah, it's not.
It's still not.
Yeah, just go ahead and maybe stop sharing and then restart. Oh, yeah, there you go.
Go now?
Yep.
Okay, yay.
All right.
It's been a great talk.
So much build up.
Model calibration, yeah. Thank you, Katie. So this presentation is really a continuation of Daniel and Katie's presentation earlier today. I feel really fortunate to be able to build off of all of their work that they have done to set us up so that we can move towards systematic land model calibration. This work is part of the LEAP project, Learning the Earth with AI and Physics. It's a new NSF Science and Technology Center at Columbia University, tasked with this kind of overarching goal of integrating machine learning tools into the climate model development process. There's kind of 4 objectives up there. But ours is one part of that, the 4th component, which is to establish systematic machine learning-based methodology for calibration. I also just want to touch on that there's this LEAP Pangeo infrastructure that's being developed as part of this project that I think we'll benefit from. There's a lot of tools being developed there. And then I want to highlight that the census is a science and technology center. There's a big focus on education. And so check out the LEAP site where there's a lot of resources, and oftentimes there's trainings and workshops and a really nice seminar series. So if you're interested in this work, check out the LEAP website. So the approach that we're taking for land model calibration, I'm envisioning to look something like this. It will likely evolve. But we'll start with a perturbed parameter ensemble, think strategically about which metrics we want to try to target, use different machine learning emulation tools to then constrain the parameter space. We'll likely iterate through this process many times before we've thoroughly constrained that parameter space, and can then move towards optimizing the model and ultimately ending up with a calibrated version. So in this talk, I'm just going to go over kind of an overview of each of these components and how we're thinking about approaching each of them. Daniel and Katie introduced this well, that we're going to focus first on leaf area index, so I won't repeat that. We know that there's some biases in the CLM5. In leaf area, these figures are from ILAM. The bias tends to be high in the high altitudes and high in the tropics, high latitudes, excuse me. And then there's also biases in the timing of peak leaf area, again, kind of late in the high latitudes and maybe early in the tropics. So these are some of the biases in leaf area that we're trying to tackle with this project. The perturbed parameter ensemble was well introduced. I'm glad I don't have to re-explain all those details. But using the one-at-a-time ensemble, Katie and Daniel were able to identify 32 parameters that were most influential on leaf area. We sampled using the Latin hypercube sampling scheme so that we're perturbing all parameters simultaneously in a 500-member ensemble that was run from 1850 to 2014 on the sparse grid. And this just highlights the spread that we're achieving with this perturbed parameter ensemble and how large it is. This is the historical period in global leaf area index in the perturbed parameter ensemble on the left, compared to CMIP6 on the right. And we don't expect these things to be comparable. I just want to highlight how large the spread is that we can achieve with CLM parameters compared to the multi-model ensemble. So once we have an ensemble, we can start to, even though the Latin hypercube is sampling the space well, it's still fairly sparse. So we want to use machine learning-based emulators to kind of interpolate between those points where we've actually run the model so that we can have this surrogate version of CLM, and we can sample the parameter space, explore parameter sensitivities, and move towards detecting interactions and nonlinearities that I'll highlight, how we're using these emulators in the next step. Daniel showed something really similar to this, so I'll just move through it quickly. In the Latin hypercube in, you get Latin hypercube out, which I thought was a nice framing. So in the scatter plot, you're getting all the parameters perturbed simultaneously, which makes it hard to draw out some inferences. It just kind of looks like chaos. We want to move from the black line to the orange line. So with the emulator, we can hold all of the other 31 parameters fixed while moving individual parameters back and forth between their minimum and their maximum values. That's the green line here. And that allows us to detect some nonlinearities, as shown in the Kmax, which is maximum plant hydraulic conductivity. So I'm trying to figure out better ways to visualize this, but to look at interactions between parameters, right now I'm holding Kmax fixed at its median value while varying Jmax, which is related to the photosynthetic capacity, back and forth between its minimum and maximum. But we're still not achieving that low LAI that we're after. But if I move Kmax down to a low value, we can then get lower values lower LAI at low values of Jmax. So just going back and forth. You can kind of see how we're detecting interactions between parameters here. Another way we're using the emulators are to constrain the plausible parameter space. So once we have the emulator trained, we can run thousands and thousands of parameterizations through it and have it predict leaf area index. And if I only subset the parameter values that give me reasonable LAI predictions, here I'm looking at the global mean. I've really not constrained the Kmax value here at all. We started with a uniform prior distribution. Our posterior is pretty uniform. There's maybe a little bit tilted towards lower values, but we're not really able to constrain the plausible parameter space using global mean. So that's why we started introducing higher levels of spatial complexity, looking at different needle-leaf and broadleaf plant functional types. We can start to better constrain the posteriors for these individual parameters. So we're thinking right now really critically about how to add metrics that will strategically further constrain individual parameters. I still think this is a hard problem. So once we have defined our target metrics, constrained our posterior distributions, and we have a robust emulator that we have some confidence in, we can start to move towards different optimization techniques, which typically in other literature will typically run individual in series. So you find a new parameter set, run CLM, and then iteratively repeat that process until you've calibrated and find an optimal set. But that doesn't make sense with CLM. That iterative process will just take too long. So we use the emulator paired with the optimization techniques. In this case, I'm working with Markov chain Monte Carlo, which is commonly used. And so we use the emulator to then identify which parameterizations we expect to give us improved versions of LAI. This is still early. The scatter is pretty wild, and we want to better constrain that parameter space before we actually take these parameterizations and rerun them back through CLM. But ultimately we will, and hope that our workflow is then, that will be how we evaluate whether our workflow is actually improving the target metrics that we're after. So at any one time, I find myself constantly in tension between these three constraints and thinking through how to move forward. We have many parameters. It's a high dimensional problem. We have to think really strategically about how we sample that parameter space. We're limited by how many CLM runs we can actually perform. And then we have this really a ton of observational data sets that we can use as target metrics as well. And we want to, and those observational targets vary in space and vary in time. And we want to make sure that we're not improving one feature without messing up the others. So we're hoping that different machine learning tools can help us balance this tension or this triangle that I'm struggling with. But I think we still need to think really strategically about the methods and the workflow as we move through this type of calibration objective. So that's all I have. I think the outcomes from this work will obviously be a systematic calibration tool that will hopefully be transferable across different model configurations. We want it to be to help make the model more accessible to other communities. Maybe you want to tune the model to an individual point or a region, or maybe you have data of your own that you want to tune the model to. This will help. This workflow will help enable that type of science. And then I think there's, Katie commented earlier about how tuning the model is really how we as model developers gain insight into model processes and parameters. But if we can you end up with this intuition, but we want to make that intuition sort of accessible to the broader community. And I think part of what we're trying to achieve here is to pull out a lot of our intuition and make it visible or accessible to folks who haven't spent as much time tinkering and tuning the model. And we want this tool to obviously be valuable to you and the community, and so your input, earlier in this process, the better. That will help us ensure that we're making a tool that you all can use. I'll point you to the LEAP website again, and then a lot of this work is going to be available on the GitHub repo that Daniel mentioned for the CLM PPE. Thanks.
Questions? Go ahead, Will.
This is more of, I guess, a bigger question, but I'm curious. We've had the same problem with the NEON project, that we start developing all these resources, and all of a sudden it's where do you find stuff, and how do you rein it in? And I'm curious if you guys have thought about, you guys, I guess you as a PPE team sort of have that question, how do you get information back from the people that are using your tools? Do you have any, I spend too much time thinking about these management type questions, but how do you envision people interacting with the tools that you're developing and then contributing back to that effort?
Yeah, I think, I'm early into this process, but we're seeing in this working group meeting today how many people are using the one at a time ensemble and bringing their results back and presenting them in the model working group meeting. So I think that's fun to see. I don't know if you've had more experience with community engagement.
Yeah, Danielle asked the same question, I think, during the seminar, which is how can we better use the results that are coming back to us? And I don't think we know, but I think we have to keep thinking about that. Maybe I'll go to Rosie, who has a question. Go ahead, Rosie.
Hey, thanks, Elaine. That was awesome. So yeah, you did. I was interested. You didn't talk a whole lot about the emulator and what it emulates as a function of what. And so you had that slide where you had the kind of global mean you were trying to emulate, and then you kind of constrained that down to the needle leaf and the broadleaf trees. And I was just wondering if you could talk a bit more about how you did that. Did you just take points that were dominated by those PFTs, or how did that work? This is a thing that obviously we're struggling with in Fates collaboration as well.
Yeah, I think
I'm interested in transferable.
Yeah, we're struggling with it too. I think that's what we're wrestling with right now is we take this global mean, we find these trade-offs. What the emulator is doing is taking the input parameter space and predicting a single target variable. That target variable could be the global mean, it could be just the mean over broadleaf LAI, or I could take a combination of many different target metrics and try to have it minimize a optimization function, right? And that again, we can still have trade-offs, by minimizing the bias in the tropics, we're compensating for a bias in some other region of the world. So it's tricky. I think we can use two-dimensional emulators or machine learning techniques to maybe that will help alleviate some of the spatial issues, but we still have issues with we don't want to just look at mean state, we want to look at interannual variability, seasonality, more than just LAI, add GPP. So yeah, I think how do we combine those target metrics and pair that with the emulator tools is something I'm working on and don't have a good answer for you on yet.
Hi. Great talk, Linnea. This is a question more broadly for the PPE community, but you're welcome to jump in. I think a lot about model spin-up. I don't run CLM, but I run SIB4, which is an offline land surface model. And by far, the thing that consumes the most resources is spinning up the model initially, because we're super interested in getting the carbon cycle right. That's my focus. So I wonder, and I don't know a whole lot about emulators, so maybe it's just my lack of knowledge, but is there something that you guys have thought about that speeds up the spin-up aspect of this whole model calibration evaluation process?
I think Daniel's thought quite a bit about this, so I'll toss this question to you.
Well, I think, yeah, first of all, we use some work from collaborators at Arizona State / Cornell to do linearized biogeochemistry to get faster spin up, so it's like 140 years instead of 1500. But I think once you run a big ensemble like this, there's an opportunity for emulating carbon pools across parameter space. So then, future efforts, maybe you would have, a head start on things. But I think we're just scratching the surface on it.
Are you talking about EG's matrix technique?
Yeah, exactly,
Okay.
yeah.
I will talk to you more later.
We're just scratching the surface on it, and I think, there's a lot of work to be done there. It's something we're really interested in too.
Yeah, I'd love to collaborate on that too.
Okay. I know we're getting closer to break, but I do want to just point out Julie's follow-up question. I think is something you said, Linnea, about. She's asking about what do you mean by refining, or how do you refine the posterior distributions? So maybe that's related to the metrics.
Yeah, in this case, once I had the emulator trained, I sampled thousands and thousands of parameterizations, ran them through the emulator and said, anything within plus or minus 5% of our target LAI is good. And then I saved those parameter sets and looked at that distribution in parameter space. So those are my constrained posterior.
Mm-hmm. Yeah, and then Sanjeev, I saw you put your hand up. Do you have a quick question? But because we are due for a break.
Yeah, I have a quick question. Yeah, this is great presentation. So what is goal here? Goal is to come up with a single optimized parameter set, or goal is to come up with a kind of a range of parameter set, like 100 or 10, that does equally good job in the quantity of interest.
Yeah, I think we're thinking about that as well. Daniel did a nice job illustrating how two parameter sets that give us a good LAI might have really different parameter values, and how those two different parameter sets might respond to future climate forcings could be really different. And so obviously an ensemble is always better. At the end of the day, we may have to have one to run in CESM 3. So balancing that is going to be tricky, but I think the first phase is going to be defining a well-constrained parameter space.
Thank you.
Okay, thanks so much, Linnea. Let's thank all our speakers. We're back at 2 o'clock now.
Is it 2:30 now? Yes, 3.
crop modeling, the next 3 talks. And we're going to start with a talk from Sam Regan on observation-based crop calendars. Go ahead, Sam.
All right, green light's on. A little bit low. Hi, excited to open up the crop modeling session. I think there's going to be some cool work here. What I will be presenting is some work I've been doing on how CLM determines when crops are grown. So that's fundamentally what a crop calendar is. It's the period from the sowing date to the harvest date, right? How do they work in CLM right now? Sowing date is determined, you have these sowing windows. Each color here is a different crop's sowing window in the northern hemisphere. Southern hemisphere, they're just shifted 6 months. And so within each of these sowing windows, sowing occurs when some temperature-based thresholds are reached. And those thresholds are based on both recent temperature as well as longer-term climatic averages. As you might imagine, when the crop is planted determines a lot of things, not just for how the crop is going to do, in terms of how much irrigation it's going to require, how much yield it's going to be able to produce, but it's also going to affect regional weather, because you have evapotranspiration going on, especially evaporation from crops like rice that have a paddy or a flood irrigation style. So exactly when in the year crops are being grown is going to affect not just the crop, but also the surrounding area. And so sowing dates, these windows, are a very important part of determining that. And then harvest date is not actually determined specifically by the model. Instead, what happens is when the crop is planted, it is assigned a maturity requirement. And maturity is determined by how warm it's been for how long. And this is a measure called growing degree days. You accumulate 1 growing degree day when you are 1 degree Celsius average over the day above a certain base temperature, which depends on the crop. So as an example, for rain-fed spring wheat, the growing degree day requirement for maturity is between 1,500 and 2,000. CLM has a little bit of opportunity for variation among this, and I'm not just skewing this because I chose a very poor color scale. I chose this color scale for a reason, you'll see why. But there's not really much variation that's allowed here. I should also say that maturity isn't the only thing that's determined by these requirements. You also have other phenological stages that you transition between when you cross certain fractions of this threshold. All right, so the advantages to how this works. Sowing dates allow some geographic and interannual variation in when exactly the crops are sown. The windows, as well as how the maturity requirements are calculated, allows for long-term shifts as climate changes. But there are some disadvantages. For one, the sowing windows are only based on temperature, when in reality, in some places, moisture, whether it's soil moisture or availability of irrigation water or precipitation, that can be more important. There's only a limited amount of variation possible in harvest requirements, as I said. In the tropics, you need more growing degree days to mature. Generally, the system has been parameterized, or it was based on a system that was parameterized for North American crops. And so there's a desire to expand how well we represent other regions. And finally, the use of these sowing windows, you may end up running into boundaries as climate changes. People might want to start sowing earlier, but they're just not allowed to because of the model. So you might be asking if I've developed a better system. No, I haven't. Don't get your hopes up. What I've done is made it so that CLM can read in externally prescribed sowing dates and maturity requirements. So why would I want to do this? Well, for one, it means we can use any arbitrary crop calendar algorithm, so for determining sowing date or maturity requirement, without having to code it into CLM itself, which is pretty convenient. It allows us to participate in model intercomparisons that require the use of standardized calendars. And we can also use observation-based calendars to force the model, and in the process, learn something about how CLM works. Huge disadvantage, I should have made this font larger, the inputs that you read in aren't necessarily prognostic, right? So that means as you get farther and farther away from the present day, you might not have something that actually does adapt. And so far, they're not. So what I'm presenting today is I used some observation-based calendars to force the model, and what I'll be evaluating is how much yield and irrigation water use change, whether that's an improvement in the model, and where and how what we learn from this might be able to feed back into future model development. I'm using the crop calendar from the Global Gridded Crop Model Intercomparison, GGCMI. This was actually the last thing standing in the way of CLM participating in this, so it's pretty exciting to have done it. But as I said, so far these are just static. They're a single average sowing date and a single average harvest date, which we assume to also be the maturity date. And it's centered around sort of 2000 era, so you wouldn't want to go too far away from that in your simulations. All right, so the experiments I did, I did a long sort of default run with just how CLM determines these things by itself. I then did a shorter run covering this, what we call the baseline period. This is sort of where GGCMI says their crop calendars are applicable. So I ran the model between 1980 through 2010 and said, okay, what's the average number of growing degree days accumulated during this GGCMI season? And that became the harvest requirements or maturity requirements that I then fed into the model along with the prescribed sowing dates. So I'm not using a sowing window. I'm just saying there's a single date that the crop gets planted on every year. I'm using CLM 5.0. I'm using unlimited irrigation, which is the default. I'm doing this at the approximately 2-degree resolution. And again, because this is sort of the baseline period, that's where my analyses will be focusing. All right, so as an example of the maturity requirements that we get out of this, as I said, I had a good reason for choosing this color scale. The default, you don't see very much variation. Once you force it with the GGCMI crop calendars, you get a lot more variation, both in terms of shorter maturity in terms of thermal time, as well as longer maturity. Right? And in general, except for sort of very high latitudes, most places require actually longer maturing varieties. All right, so how does this affect yield? Here I'm just summing up the yields in each grid cell, those being multiplied by the area in each grid cell. You get global yield that way. So for wheat, this increased the bias a little bit. There was a slight 0.3 of a ton per hectare bias. Now it's 0.7, but that's not really a huge difference. Corn and soybean were barely affected at all. But cotton and sugarcane, so I should have said, the aqua here is CLM default, and the pink is prescribed calendars. Cotton and sugarcane saw huge increases and actually really radical improvements in the global yield numbers. And rice also saw a really huge jump, but it's a performance degradation. It was a little bit underestimating, and now it's pretty strongly overestimating. We'll get into this. So to start explaining this, I wanted to look at where is responsible for these changes in production. Cotton was India and China, but I put it small here because the new 5.2 data sets that Peter's working on have cotton in different places, so I'm not worrying about that for now. I'm just going to focus on rice and sugarcane here. So rice, it's mostly India, Thailand, and China, where you see a lot of the increase happening. In sugarcane, there's one grid cell in India that's the strongest by far, and then it's harder to see, but there's some in southern Brazil and also the Caribbean. All right, so what's causing the change in yield for rice? In the original CLM default run, you have rice in the northern hemisphere and in this region of interest being planted in the first part of the year, the first 100 days or so. According to the GGCMI calendars, they should actually be planted closer to the middle of the year, the second 100 days. And so when we force it with the prescribed calendars, we actually see a shift of 45 days or more in China, even more than that in Southeast Asia, And in India, it's as far shifted as it can be, about a half year. So that you're being planted in much more favorable seasons, and you actually end up having very fewer failed seasons. So the default CLM run, you actually have a very low proportion of your harvest actually reaching maturity. There's a maximum growing season length in CLM, and that gets hit before the necessary heat requirements were being accumulated. So now with the prescribed calendars, you actually end up getting maturity almost 100% of the time, especially in these important high-producing regions. With sugarcane, the problem was that the plants were maturing too fast, so they weren't in the ground long enough photosynthesizing. That's why the yield was far too low. So what we're looking at here is a map of growing season length. In those important regions, growing season averaged about 100 to 175 days, according to GGCMI. Once I forced it with the prescribed calendars from GGCMI, we're now looking at the 175 to 300 day range. So twice as long, you're going to get a lot more yield. But I wasn't actually able to use the GGCMI calendars because those actually assume a 364-day season in a lot of places. And I was still respecting CLM's maximum 300-day season. So you end up hitting that 300-day mark, this orange, in a fair amount of the area, including some of this India region, which is where we saw the huge increase. So that's still a little bit of a weird limiting factor, but overall, I mean, as I said, we saw a really good improvement in the yield performance. All right, now what about irrigation? We have less irrigation with the prescribed calendars. We went down by about 13%, and that's mostly due to rice, a little bit due to corn and soybean, and then cotton, sugarcane, and wheat went up a little bit. But overall, we have a decrease in total required irrigation. That seems like it would be going the wrong direction because CLM actually underestimates irrigation. But that's using the default technique for irrigation that's in CLM right now. If you use more realistic irrigation techniques that were developed by Yao et al. In a paper last year, it was really cool. They added like paddy irrigation and flood irrigation. And they ended up actually getting a little bit of an overestimate by about 15 or 20%. So if I were to pair the prescribed calendars with these new irrigation techniques, it might bring us closer to the actual expected value. So learning from this, we can use, instead of these hemispheric sowing date windows, we can have grid cell specific sowing date windows centered on the observations. We can pretty much just use those maturity requirements that I derived here straight up. Would probably want to scale them based on decadal climate averages so that we get that shift over time. And we might want to replace the growing season length, the maximum growing season length parameter, with a more flexible behavior that's, for instance, if no photosynthesis occurs for a week, then you harvest, something like that. Thanks.
Questions for Sam? Yeah, go ahead, Emmy.
I'm curious about two things. One, is it an okay assumption that the harvest date is the maturity date? That those are the same? And then two, I know that a lot of crop models do use growing degree day type metrics for end of season, but like we have a plant model, can't we do better than that?
We have a plant model, yes, but we don't have a crop specific plant model. There are a lot of, so just the way that like grains develop, like the number of grains and then the filling of the grains happens, it's still a little bit stylized in CLM. So that's why the growing degree day thing still happens. But even in the models that have a more sophisticated physiology, there's still a pretty big dependence on growing degree day, just because it's a really good proxy for the metabolic processes that need to happen for maturity to.
Yeah, I mean, I guess it would be mostly the same, but it does feel like maybe we could add in, because we are representing a little bit more, some modulation on that.
Yeah, probably. But I think we have, as I showed, there are some pretty impressive gains in performance we can get without
Yeah, and then what about the maturity harvest date thing?
It's probably a good assumption for, at least for industrialized countries, where you have the ability to harvest large areas pretty quickly, right? It might start to break apart in places where harvest is less efficient. And it also might not apply so much for certain kinds of crops. And for example, fodder corn doesn't have to be harvested at 100% maturity. Like you can feed it to cows if it's only 80% mature or whatever.
Or I think in the other direction, they would just leave it in the field.
Yeah, that's also possible, for sure. But yeah, probably not too much longer after maturity, I would think. Because farmers are pretty good at, looking at a crop and saying, oh yeah, this is ready to go.
Peter, go ahead.
Okay. Sound great. I was wondering about like time-dependent sort of like cropping windows. Do you think, like, because we currently have time-dependent fertilizer and irrigation as well as the data sets, would you think that it'd be possible to have these scenario-dependent windows that moved?
It's possible for sure, but I think the beauty of the sowing window is that it allows sowing date to move, right, within the sowing window. I think that the legwork that would be necessary to come up with a way to shift sowing windows would be better spent developing a more generalized method for determining when sowing date happens and just moving beyond the window entirely.
Cool. All right, thanks, Sam. I think we'll move on. Our next talk is by Olga Dombrowski, CLM5 fruit tree.
Thanks.
Yeah, okay. Great, perfect. Go ahead.
All right, hey everyone. So I'm a PhD student from the research center Jülich in Germany, where we're also quite a big group working on CLM5 related topics. And yeah, but I decided to temporarily switch to like much better weather and much better views of the mountains. And yeah, visiting NCAR for 2 months. So I'm really happy to be here. And yeah, I want to introduce you to a new submodel within CLM5, which is called the CLM5 fruit tree, which were developed to include deciduous fruit orchards in CLM5. So why should we consider deciduous fruit orchards in land surface modeling? So on the one hand, as you can see here on the example of apple, there's like production of fruit orchards like basically across the globe. And they also have significant economic importance and also shape like local landscapes in many areas. And at the same time, they can provide a variety of ecosystem services. So for example, fruit production, climate regulation through mitigation of greenhouse gas emissions from the soil, water regulations. And yeah, so those ecosystem functions that drive those ecosystem services, they depend on interactions of climate and soil, and also depending on the management practices in the orchards. So yeah, and then like in this system, the orchards themselves then also influence soil, water, and climate. So it seems like if we want to account for their role and this functioning, we should include them in our models. So like the concepts that we used to develop CLM5 fruit tree, the idea was kind of to draw as much as possible from the already existing characterizations of vegetation in the model. So we have the annual crops on the one hand and natural vegetation on the other hand that's already represented in CLM5. So from the annual crops, we have some characteristics that are shared with the fruit tree. So we have different like crop growth stages that are implemented. Then we have a harvestable organ. And we also have main crop management practices such as fertilization and irrigation that we can use also for the deciduous fruit tree representation. And then on the side of the natural vegetation, we have the deciduous trees that are represented. So there we have this dormancy period that's typical for this type of tree. And then we also have the growth and turnover of woody biomass that we can also use for this development. And then we included some new processes and changed some. So in the phenology subroutine, especially, we want to represent the orchard life cycle. So we start with transplanting of seedlings that have some initial biomass to like a full orchard rotation when it's reaching its lifespan. So basically there's like a clear cut and then a reestablishment of the orchard. And yeah, then for the seasonal deciduous phenology, you want to capture this transition from dormancy period to the active growth period, and also like this long canopy duration and growth, and like the parallel fruit growth. Then we did some changes to the carbon nitrogen allocation scheme. So here specifically to capture like the reserve dynamics that are characteristics for deciduous species next to the direct growth. Then also represent the fates of carbon nitrogen in the system. And then lastly, we also implemented a winter pruning as a management practice. So for the phenology, so the fruit tree starts in winter as like being dormant, and then to represent the chilling requirements that deciduous species need actually to exit dormancy, I implemented the sequential model that first accumulates a certain amount of chilling days until it reaches a chill requirement, followed by anti-chill days, which then triggers bud burst. And then bud burst sets off the growing degree day accumulation. So Sam already explained the growing degree days in his talk. So like the remaining crop growth stages that either drive fruit development or the development of the vegetative organs, they are like governed by growing degree day thresholds. And then finally, senescence is triggered just by simple temperature threshold. So whenever the mean temperature goes below a critical temperature threshold, senescence is triggered. Yeah, for carbon allocation, so now there are like different pathways that the assimilates can take basically depending on what time in the growing season we're at. So early in the growing season, the carbon that's stored in the plant basically drives or enables the growth early in the growing season. Then in the main season, the carbon assimilates, most of them directly contribute to the growth of the plant. And then late in the season, the assimilates are actually mostly used to refill the carbon reserves that then enable growth in the next season again. And then for the individual plant organs that are represented separately, they have different fates in the system. So we have the fruits that are being harvested and then exported. We have leaves and fine roots that feed the litter cycle and eventually turn into soil carbon. We have part of the wood above ground biomass that's removed through this pruning management practice, and then the remaining woody biomass stays on the field. Yeah, so we then parameterized this CLM fruit tree for apple orchards, and we used, we were collaborating with a group in northern Italy that had like a really nice multi-year data set on an irrigated apple orchard. So we had like management information, yield, biomass, LAI measurements, carbon nitrogen ratios, and also multiple years of eddy covariance flux data. And we used these measurements and combined them also with literature values. And I also did like a simple one-on-one sensitivity analysis to sort of get a feel of what are these sensitive parameters that we should be looking at to come up with this apple plant functional type, currently using the PFD 3536, so like irrigated, non-irrigated, that has like crop-specific parameters for the main crop parameters here. Yeah, to show you some results, so you can see leaf area index for 3 years starting from 2010 on your right, and then to the left you can see 6 years of yield data, comparing the orange the simulations and green the observations. And yeah, basically from the LAI data, we can see that we're actually pretty well capturing the canopy duration and also the amplitude of the LAI. And if we look to the yield data, we see that CLM simulates somewhat lower interannual yield variability. So if you look at the years 2012, 2015, kind of stand out. But yeah, on average, the yield is really well captured. I then also looked at the seasonal ecosystem fluxes in the orchard. So this is just an average of 3 years of observations and simulations. So you can see here the carbon fluxes on the one side and then the energy fluxes on the other side. And you can also see here that the model agrees really well with like capturing the growing season, the start and the end, and also the magnitudes of the fluxes seem pretty well captured. If you look here to the lower right, it seems like the model has somewhat lower variability in the ecosystem respiration flux. This may be related to the alley vegetation in the orchard. So those orchards typically have grass cover that's actively growing in the alleys, which is also being managed. So it's being like mowed a couple of times a year. And we're not simulating that, which may be causing some differences in there. Then also, if you look to the sensible heat flux in the lower left, we see like a negative model bias in the sensible heat during the summer, which actually corresponds to like the irrigation season. So that may be like an artifact of like very strong evaporative cooling that's happening in the model. Yeah, those are the same fluxes, just like scatter plots of those fluxes again, carbon fluxes and energy fluxes. Yeah, we mostly see really good model performance and good correlations with low biases. Just for the ground heat flux, we can see that actually the simulations have a bit of a bigger spread in the data, and we think that could be also related again to like the effect of the grass cover, which may have actually like a dampening effect on the ground heat flux in the observations, which we're not capturing in the model at this stage. And then also, yeah, we see some more variability in sensible heat, which could also be related to difficulties in radiation partitioning in the model, since we have this really complex discontinuous canopy in the orchard, transitioning between the trees and then the grass. Yeah, so what are the takeaways from this model development? We were able to represent biomass and seasonal dynamics of the ecosystem fluxes pretty well. We may be able to improve the model performance if we consider the vegetation and also this additional management practices that go along with this. Yeah, we may have some model weaknesses in partitioning the energy correctly in this canopy. And yeah, so this was development on one side. Obviously, it would be nice to have more test sites, different locations to see if the model holds up, basically. Yeah, this development was written up in a paper that was published last year in GMD. And just to end, I want to quickly show you some of the ongoing work that we're doing with CLM5 fruit tree in a Greek catchment, where we're actually focusing on irrigation. So we have the model set up on 2 single point sites in Greece that we have equipped with a bunch of sensors. So we're measuring, we have a weather station, we're measuring soil moisture with a dense soil moisture network, with subflow sensors, some other measurement devices. So we want to apply the model to those 2 sites, and then also assess and see if we have to maybe adapt the irrigation routine within CLM5, and then in parallel also doing a regional case simulation of the wider catchment. It's called the Peneus Hydrologic Observatory. So it's encompassing those 2 sites, and they're also looking at regional water resources in terms of crop water consumption and the irrigation requirements and how they may develop in the future. And yeah, thank you very much, and I'm happy to take any questions.
Questions? I did have a question about the management and the pruning, and maybe you could say a little bit more about how that was parameterized. I'm just also thinking of Josh's talk about forest management. I'm wondering if there's any parallels.
Yeah, so the pruning, well, we saw it from the data set that we used for the development, that basically a lot of the biomass that is growing every year is removed again by the pruning practices. So it was around 85% of the newly created biomass that's being removed. So I kind of just used that 85%, but it's also the user can adjust it if that's something they know that it's a different amount there. And yeah, and then actually the pruning residues can be handled in one of 2 ways. So either they can be exported from the field, or they can be reincorporated into the soil. I actually saw that this made quite a difference in ecosystem respiration if you export them or integrate them into the soil. Yeah, but in reality, actually, the pruning practices influence also yield, etc., which at the moment is not happening. So at the moment, the pruning is actually just managing the total amount of biomass that's on the field, and to just
I think it's really cool how it's a really nice development addition to the model. Super cool. But I'm curious, but the next question is how do we take it global? How do we do more than apples?
Yeah.
I think lots of people have talked about woody crops in CLM, so it's really awesome. It's so exciting to have a framework to do that under. And I wonder, is it too highly, I think your approach has been awesome, but how hard is it to abstract and make it less perfect but more global?
Yeah.
Is that dangerous, or is that
Yeah,
something
no,
you're-
I definitely think you have a point there, yeah. I think the challenge is that there are not so many like well-equipped sites where we have good data on fruit orchards. I mean, there's a lot of study being done on fruit trees, but mostly like looking into flowering dates and how those change with climate change happening. So, but there's like very little flag sites, for example, so that's going to be a challenge, yeah. I mean, I think I'm supposed to talk louder, I think. So yeah, the development in itself, I think, I mean, it captures some of like the main processes that are similar to all deciduous fruit trees. So I think in that, definitely it can be used. Regarding the parameters, there's definitely something to figure out how to come to some in between that maybe encompasses more of the deciduous fruit tree species. We actually have, like, even within the apple trees themselves, there's so much variety because there's so many different cultivars, and also they change a lot on how much of the carbon is actually allocated to the fruit and how much their yield is. So there's like a lot of variety. I think that's going to be challenging, yeah. To come up with some parameters that may be like a good mean of all of those.
Okay, thanks, Olga. Maybe we'll transition. We have one more talk in the crop model section. It's a remote talk. So we're going to get that set up. And maybe Tyler, you could dim the shades just for people in the room. It's getting a little bit bright. So I'm going to stop sharing. And Hydron, if you're online, you can go ahead and share your screen.
I'm gonna try.
Cool.
Okay.
That's good. Go ahead. And great.
Okay. So yeah, from things being grown, we're gonna go to things being eaten. And yeah, so I tried to make this a little provocative, saying like, have reindeer eaten all the shrubs. But the base idea of this talk is how can we mimic Arctic big grazers in CLM? And so the reason why we want to do this the research is based within the framework of a project called Charter that looks at drivers and feedbacks of changes in Arctic terrestrial biodiversity. And one of the ideas in Charter is that we want to simulate future effects of socio-ecological changes for indigenous and local communities and for traditional livelihoods in the Arctic. And within this framework, Charter has been looking at reindeer herding as a specific form of biogeoengineering because big grazers like reindeer or caribou shape the environment that they live in. And there are a number of studies on this, and some of them, for example, suggest that herbivory might counteract the effect of a warming climate in the abundance of rare taxa, or in general, in, for example, the shift of specific types of vegetation. And also there are some studies that suggest that large herbivores might be able to protect permafrost in certain areas of the Arctic. And the specific question that we want to look at is, what would a climate change shaped future look like with very low numbers of reindeer versus very high numbers of reindeer in the Arctic? And in order to do that, we need to somehow put reindeer in the Arctic, which was very simple in this image, but in reality is not so straightforward. So just to give fair warning to people, what this talk is about is like the feasibility of mimicking big grazers and like discussing the plausibility of the approaches that we might take with you as the experts in this model. What this talk's not about is model results, because I haven't done anything yet in this direction, so that will have to wait for next year. So basically now, this is what I would like to have, but reality looks like this. So what we need to think about is, what impacts actually do large herbivores have on the Arctic environment? And in the first step, we've tried to look at animal behavior that affects the environment. And there are a number of things that came up, like browsing, grazing, effects on wild animals, defecating and trampling, and then what are the environmental impacts of these animal behavior. And you can see that this already here looks quite chaotic, and a lot of things impact on a lot of other things. But the base impacts that we think are relevant are impacts on vegetation structure, on biomass removal, on biodiversity, fertilization, on snow, and on soil compaction and erosion. And in the next step, we've tried to look at model parameters that we can change to actually mimic the impact of the animal behavior on the environmental parameters. And this is like what is colored in green is the things that we've decided that we want to explore for various reasons. So plant functional type distribution, background albedo, snow compaction, soil color, and soil organic matter content. And now the question is, how do we modify the parameters? And so the way in ecology this is usually approached is that you go out into the landscape and build up fences that exclude reindeer from certain areas, which makes these exclosure sites. And there are a huge number of studies like this. And basically, most of them tell different stories, because this is obviously very dependent on the ecosystem that you exclude the reindeer from. But some of the effects that are found seem to be common in all study sites. So if you exclude reindeer, you will have more shrubs, you will have more lichen, you will have thicker organic layers because you remove a source of erosion, and you will have lower snow densities because there is no trampling. So these are the parameters that we want to focus on, and I'm just going to try and explain our thought process in how we might do this. So first is the easier things. We want to increase shrubs, and I've looked at a number of studies, and a reasonable increase of shrubs in exclosure sites seems to be around 15% in comparison to an ambient non-grazed site. So we can go and look at the CESM standard distribution for boreal deciduous shrubs, and we can increase it by 15%. Then it looks like this. Very luckily, there were no grid cells that had shrubs above 85%, so I could just do this everywhere. But then for the PFTs to add up correctly, I need to decrease other PFTs in the process. And from the exclosure studies, the suggestion is that we should remove grasses. So I went for Arctic grasses, and then if you reduce them by 15% everywhere, you end up with these red areas where that's not possible. You can go for C3 grasses, but that doesn't account for all of the areas as well. So in the end, in the increase of the shrubs, I just focus on the areas where I can increase them by 15% by reducing the grasses, because I don't want to reduce forest. Because that is an impact that reindeer don't have, so they don't decrease the abundance of mature trees. So this is shrubs. The other thing that is, in a way, straightforward, I think, is the increase of lichen abundance. Since there is no representation of lichen and CESM yet, and tundra is mostly represented as a mix of bare ground and grasses, we thought that we could try and mimic the effect of lichen by changing background albedo in areas where there are, or in grid cells where there is bare ground. The reasoning behind that is if you increase lichen cover by around 10%, which is like, again, one of the medium numbers shown in studies, then albedo increases by around 0.02 to 0.01 to 0.02, which is, if you look into this table that shows the soil color class visible and near infrared albedos in CLM, this is around the shift between one soil color class and the other. So we've decided to just shift the soil color class by 1 to mimic this impact of an increased lichen abundance. Now we go to the more complicated things, snow density. This has been done before, actually. There's a study by Christian Beer who tried to look at possible protection of permafrost soils from thawing by increasing herbivore density. And what he did in his study is he wanted to look at a very high number of herbivores, and he modified the snow compaction scheme in his model to actually mimic trampling. And the point is that we cannot really use this approach one-on-one because CESM has a more complex snow compaction scheme than the model that was used in this study. But I still thought that maybe we could, like in this equation that uses the final soil compaction factor, we could introduce an additional multiplication factor that decreases the snow compaction. The other thing that we came up with is we could like modify the ingoing density of freshly fallen snow to decrease the snow density. But this is still like, I'm not sure that that's the way to go, but those are the ideas that we had. And then there is the organic matter discussion. So exclosure sites actually have thicker organic soil layers, but the carbon storage of ambient non-grazed sites and exclosure sites was actually pretty similar throughout all the exclosure studies that we could look at. So what do we do with this information? We could increase the organic matter content of the top soil layer, but if you look at the organic matter density of the top soil layer, there is not much room for increasing anything. And also doing that would mean that we increase the overall carbon storage. We could also try and move some of the organic matter in the deeper soil layers somewhere up into soil layers that are closer to the top. So if you like go to soil layer 3, for example, there is room to increase organic matter density. That would keep the overall carbon storage similar and would like increase the organic matter in the top soil layer. But I'm also not sure if this is the way to go, or maybe someone has a better idea on how to approach this. Yeah, so basically these are the things that I actually wanted to show, and I wanted to keep this short because I want your input on what I've just shown you. So there is only like this one slide that kind of summarizes what I've just shown you, and I'd be happy to answer questions, and I'd be very happy to get suggestions.
Questions? Go ahead, Claire.
I'm the wrong person to give suggestions, so I just have a question. I was curious about the mechanism behind why excluding reindeer leads to thicker organic soil layers. Like, do you think that changing the shrub abundance would propagate to the soil?
So the way this narrative goes, and I can just repeat what I've read in studies, right? Because I'm no ecologist, but the way this narrative goes is that actually excluding reindeer reduces the effects of trampling, and trampling is what erodes the topsoil layer and therewith removes the organic from the top of the soils.
Okay.
So it's not actually, I mean, there are certainly also interactions with then the abundances of different types of vegetation that occur if you exclude reindeer. But the main narrative on explaining this is on reducing erosion.
Thanks.
Yeah.
I guess I have a question and a suggestion. And maybe this is the suggestion. So like the organic horizon in CLM will change with the CTSM 5.2 data set. And you actually should be able to increase organic matter content slightly. It won't be as saturated as it is in the current data set. And I guess that your concern about changing carbon doesn't really matter because the organic matter that's read in for hydrology is different than the carbon that's being simulated for carbon storage. And so you can kind of disassociate the carbon cycle effects from the hydrology effects because of the way that the model runs.
Okay.
And then I guess the FATES team is also having discussions about grazing, and I don't know as much as we can. I think it would be awesome to put grazers into, like, to create grazers in a model once, not 4 times. So maybe my other suggestion would be to open a conversation with the FATES team too about this topic. Yeah, that's it.
And Hannah Lee, right?
Yeah, that's right.
Yeah. She's also working on it, yeah.
This stuff is going.
I was just gonna, the suggestion for snow density is, since everything comes back to the PPE these days, is that we do have snow parameters in there, and there should be snow parameters that could be adjusted related to the snow compaction, which you should be able to adjust your snow density through parameter values.
So what do you have like a specific suggestion where
No.
we should? Okay.
No, but we have the data set there, so we can just screen for, use Daniel's tools to look for the top parameters that affect snow density and pick the top one. So it'd be easy to do, so we could get back to you.
All right, thank you.
Okay, thanks, Hydra, and I think we'll move on. So we're gonna go straight into our urban model session now, a little bit early, but that's okay. We have 3 talks. I believe they're all remote, so hopefully there'll be some smooth transitions. So Joyce, if you're online, you can share your screen. Joyce is gonna talk about climate-driven, urban, humid heat exposure and cooling challenges.
Great, thank you so much. Okay, can you see my screen?
Yeah, it looks good.
Thank you. Hi everyone, thanks for having me. My name is Joyce and I'm a PhD student. And today I'll be sharing some of my research with my advisor, Lei Zhao, collaborator Keith Olison, where we representation in CESM to study climate-driven urban humid heat exposure and cooling challenges. So cities uniquely contribute to, are exposed to, and also have a strong capability to adapt to climate-driven risks, one of the most serious of which is future heat stress under climate change. Both climate change and urbanization tend to result in higher air temperatures and lower relative humidity in urban areas, 2 trends with opposing effects on human perceived heat stress. However, the combined impact of these processes has not really yet been studied on a global urban scale. So this is where CSM is really helpful. So it's one of the few state-of-the-art global climate models currently with explicit urban parameterization, which enabled us to study the interactions between large-scale climate change and local-scale urbanization. We had 2 main goals. The first was to assess future changes in exposure to and drivers of urban humid heat stress. And the second was to look at climate-driven cooling challenges and the impact of climate change on cooling with urban greenery. So we ran 2 simulations. The first was a historical one, and the second was a projected future climate under SSP3 RCP7. And we used a temporal resolution of decadal JJA means for the first and last decades of the century. For variables, we looked at urban wet bulb temperature as a proxy for urban humid heat stress and also overlaid this with urban population projections by Jones and O'Neill for the same SSP3 scenario. And for future cooling, we looked at 2 main variables. The first was long-term average JJA precipitation as a proxy for irrigation needs. And the second, we proposed a simple proxy for cooling efficacy of urban greenery. And this we quantified as the difference between dry bulb and wet bulb temperature, where the idea is the larger the difference between those, the more efficient or effective cooling will be. Okay, so moving on to some of our findings. The plot over here shows projected urban wet bulb temperature at the end of the century, and the stippling indicates areas with projected frequent high humid heat stress. So basically, we find that urban humid heat increases globally despite projected urban drying. And here we also highlight 5 general hotspot regions. For comparison, this is projected air temperature under the same scenario. And you'll see that although there's similarities in the hotspot areas, using air temperature alone could potentially underemphasize areas with high heat and humidity. And then we brought in the population projections, and you'll see that there's pretty significant regional variation in terms of current, so that's the top bar, and future, the bottom bar, exposure to high humid heat stress. And for some regions, such as the Western Africa, Southern Asia, and Southeast Asia hotspot regions, the growth in urban exposure to high humid heat stress is significantly faster than that of the total urban population. So next, we wanted to better understand these increases in urban humid heat. And to do that, we decomposed increases in wet bulb temperature into the contributions from air temperature and relative humidity using an empirical relation suggested by Stoll. And then we further decomposed relative humidity into the contributions from air temperature and specific humidity. We then grouped the air temperature terms and decomposed the changes in air temperature and specific humidity into the contributions from urbanization and climate change. And then that brings us to these 4 terms. So using our simulation outputs, we did the decadal mean urban variables for the 2090s minus the same for the rural 2090s to approximate the urbanization impacts. And similarly for climate change, we did rural for the 2090s minus rural for the 2000s. So these are the results of our decomposition globally on the left, and then here we show the decomposition for the 5 hotspot regions. And basically we find that the increase in global urban humid heat is largely driven by increases in specific humidity due to climate change. So that's the filled in blue bar, followed by air temperature driven by climate change. So that's the filled in yellow bar. And this difference is actually a lot more striking for the 5 hotspot regions here, which are all located around the tropics, than it is globally. So we thought that was pretty striking. And in terms of the urbanization impacts, you'll see that there's some regional variation in that. So that really depends on both the local urban and the local rural characteristics. And this decomposition really highlights not only the importance of humidity, but also that local adaptation strategies may be insufficient in the absence of like global climate change mitigation. Okay, and then moving on to the cooling side. So in this figure on the x-axis, we have long-term average JJA precipitation, and on the y-axis, we have present day cooling efficacy using the proxy we proposed. And we find a general globally consistent pattern where cities with higher cooling efficacy tend to have lower precipitation and potentially greater irrigation needs, whereas cities with ample precipitation tend to have lower cooling efficacy. And then the little figure on the top right shows the change in these 2 variables under climate change, and you'll see that many cities are projected to have increased cooling efficacy under climate change, but less precipitation to support this cooling. And finally, we wanted to highlight the potential for urban-specific variables to guide climate-conscious decision-making in cities, and maybe to help us identify groups of peer cities with similarities in key mechanisms affecting climate change adaptation. So in this case, we're looking at urban humid heat stress. The figure in the middle shows future cooling efficacy for cities with statistically significant changes in both precipitation and cooling efficacy. So at the top, we highlight two cities in Saudi Arabia, Jeddah and Riyadh, and these two cities are pretty similar in terms of location, country, culture. They both don't get a lot of rain, but Jeddah has a much higher projected wet bulb temperature and lower cooling efficacy. So this suggests that lessons learned about cooling strategies in Jeddah, what works, what doesn't work, stuff like that, may not always be applicable for planners in Riyadh. Whereas the cities on the bottom, Bucaramanga in Colombia and Hanoi in Vietnam, they're more diverse in terms of location, culture, country, etc. But you'll see that they have pretty similar projected wet bulb temperatures, cooling efficacy, and precipitation to support that cooling. So we suggest that recognition of these urban-specific variables can really help support and improve the applicability of knowledge sharing across cities as we try our best to adapt to climate change. Okay, so this brings me to a quick wrap up of quick takeaways. So humid adaptation is urgently needed in general, but especially in tropical coastal urban areas. Humidity is not only a major variable in human perceived heat stress, but also a key driver of future increases in urban humid heat. Cooling solutions are impacted by the same climatic change driving the very need for cooling. And urban explicit projections of future cooling contexts are crucial for improving the resiliency of future urban cooling and knowledge sharing as cities try to improve their livability under a changing climate. So that's the end of my presentation, and I want to thank you guys for your time, and I welcome any questions, comments, or suggestions. Thank you so much.
Questions in the room or online? Is there something in the chat right now? I just see blue.
No, there's not.
Oh, go ahead, Sam.
I'm not just saying that because I want to ask my question. Hi, Joyce. This is really cool. Earlier today, I actually started thinking about, in the context of my crop calendar work, how it might affect humid heat. And I was wondering, did you, was this run with the crop model enabled?
I would have to check on that, but I don't think so. And that would actually be really interesting to look at. I think I have come across some studies where they're looking at areas with really high levels of irrigation, and they found that that actually impacted the local humid heat stress. So I think it'd be really interesting to run those two things together and see how they might interact actually. So thank you for bringing that up.
Cool.
Yeah, Joshua?
Very nice presentation, and I'm not very familiar with this stuff, and I feel like I understood almost everything. The only thing I didn't quite understand is on your that first map that you have on the far left, I could tell that the bottom bars under climate change were longer, but I don't understand the distinction between, no, you went past it.
Oh, sorry.
It's the other one.
Okay.
Yeah, what is the difference between the exposed and not exposed? What is that?
Oh, so that's a great question. So basically, we just selected a threshold where above that threshold, it would be like much higher humid heat stress, and then below that threshold would be not exposed. But you could theoretically try different thresholds and then see how this figure would change. So also for this study, we were focusing more on chronic humid heat stress as opposed to extreme events. So we were looking at decadal JJA means for this project.
Thank you.
Thank you.
Okay, thanks so much, Joyce. I think we're gonna move on. Thanks for sharing.
Thank you.
Okay, so our next talk is by Xincheng Li, also a different talk. Xincheng, go ahead and share your screen.
Sure. Can everyone hear me?
Yes, we can hear you.
Perfect. And is my screen showing up okay?
Sure, you can put it in full screen.
Yep.
Okay, thanks.
All right. Thank you everyone for coming to listen to my talk. I am Xincheng Li and I go by Kathy. I'm a fourth year PhD student in the UIUC working with Professor Lei Zhao, same as Joyce. Today I'm going to introduce our project on elevated urban energy risks due to the interactions between climate and energy, specifically climate-driven biophysical feedbacks. When we talk about climate and energy interactions, we're mostly familiar with the classic biogeochemical feedback, where energy use induced greenhouse gas emissions cause global warming. Most global scale HAC projections consider these effects and other socioeconomic drivers, and there has been a consensus that socioeconomic factors such as population growth and economic development would be the driving forces for energy demand changes. However, an overlooked energy-climate interactions in these projections happen between the HAC energy used and the local urban environment through the biophysical feedbacks. The use of heating and air conditioning causes waste heat to be released into the urban environment, warming it and in turn affecting HAC energy use. This matters because the presence of such feedback loops means that the relationship between HAC energy use and climate will depend any present-day relationships derived from historical observations will break down under warmer climates, and simply extrapolating from these relationships will not capture the complete impact of climate change on energy. Although most current global scale projections are made with the statistical methods, past climate and past HAC energy use give empirical models its parameters, and it's fed with future climates to make future HAC projections. Although these are computationally inexpensive, they cannot capture the feedback effect, as we talked about. An inherent assumption to these methods is that what happened in the past will happen in the future. This is likely questionable in the long run, especially under decades of climate change. If we want to understand these feedback effects, we will need to use dynamic models. And some studies use building energy models, but they're driven by weather data files. And this would face the same problem as the statistical model, where it cannot reflect the two-way interactions between climate and energy. Unless the BEM is fully coupled with the regional climate model. So this way, they exchange states and fluxes at each time step to capture the two-way interactions. But the drawback to this is it's usually very detailed and computationally expensive to apply over large scale and over the a long projection period. In this study, we use CESM, which is one of the rare Earth system models, to have a physics-based urban representation, and it has integrated building energy model, where it captures these heat transfer processes in and out of buildings, calculates and outputs HAC energy demand directly. The waste heat generated from HAC energy use is added back to the urban environment. This completes the feedback loop and allows us to make global scale projections capturing these feedback. We're able to make multi-model, multi-scenario projections through the integration with physics-guided machine learning. We use CESM2's future climate and energy response to train and validate neural network models, which become our urban emulators. We then supply these urban emulators with climate realizations from other Earth system models to make urban scale projections for under those climate realizations. Because our emulators were trained on coherent future climate and urban energy responses, the two-way biophysical feedback are intrinsic to the emulator parameters, so we're able to capture the feedback effects while being computationally inexpensive. As our goal is to delineate effects of climate-only effect, we kept socioeconomic factors at the present state to isolate the climate-driven impacts. We find through the time series of global annual mean changes that urban temperature on average increase by 2 to 5 degrees, depending on the scenario, and the multimodal uncertainty increased marginally throughout the century. But AC demand diverges around mid-century between scenarios and becomes more nonlinear and uncertain towards the end of the century in the higher emission scenarios. This is not observed for heating demand. The decrease is closer to a linear behavior and the uncertainty stays relatively constant as well. This is also reflected in the time series of HEC temperature sensitivities, which indicates how much HEC energy demand will change given 1 degree of temperature increase. We see that after the initial fluctuations due to the small temperature change values being divided, air conditioning energy becomes more sensitive to temperature towards later in the century and under higher emission scenarios. This is a behavior we would expect under a positive feedback. Heating temperature sensitivity converges between all scenarios. This demonstrates that extrapolating from current temperature AC energy relationships to project into the future risk underestimating future AC energy demand, especially under higher emission scenarios. We also compared our results with the prevailing degree day methods, widely used by empirical models and adopted in IPCC, the 6th assessment report to inform policymaking. As degree days reflect only the one-way effect from climate to energy, this comparison shows impact of ignoring such feedback. We find that under SSP 585, degree days shown in gray here project about 100% increase in AC and 25% decrease in heating, while our results shown in orange and blue here project about 220% increase in AC and 47% decrease in heating, with much wider range of uncertainties. This shows that ignoring biophysical feedbacks risk underestimating both the magnitude and uncertainty of future HEC energy demand changes. The demand projections will need to be made explicitly using dynamic models to capture the full scale of climate impact. The effects of biophysical feedback are also reflected in the spatial variability. Here we show changes between the beginning and the end of the century, with colors indicating the magnitude and stippling showing there's a good multimodal agreement in these regions. We see smooth spatial transitions in temperature changes under both scenarios, with over 70% of a global urban area having good model agreement, where AC and heating shows much more spatial variations and models don't agree on their projections over most of the global area. This is not something we observe in temperature or degree day projections. This shows even when models agree on temperature projections, they can differ substantially on HEC energy projections. Cities may need to prepare for less certain energy future than they previously had thought under degree day projections. We also compared cities with similar climates or urban characteristics to highlight the unique challenges faced by them. On screen here are 4 pairs of cities' HEC energy response curves, except that it's multimodal results, so we can see the multimodal uncertainty here. Top 2 pair share similar climates and warming, but have different buildings and HEC ownership rate. Miami and LA has nearly saturated HEC adoption, while Essence have less, and Jakarta has a very low AC adoption, which is why we see virtually no response of AC or heating to temperature change. This means that given rapid urbanization and economic development, Jakarta's demand response will likely morph towards their more affluent counterparts. On the other hand, cities with similar urban and building characteristics can face diverse challenges due to their different background climates. Climate warming may help cities in colder climates like Tehran to save energy in the heating season, but challenge cities like Riyadh, where climate is warmer, to have increased cooling demand and possibly uncertain increase. However, even with similar background climates and HEC ownership rates, The demand response could still differ in their multi-model uncertainty, as shown by the AC response between Hong Kong and Chongqing. Multi-model projections are thus essential for cities to understand their possible energy futures and plan accordingly. That was the project we wrapped up, where we looked at the climate-only effect on biophysical feedbacks and how it affects future urban energy response. And we're working on integrating also the socioeconomic side of things, where population grows, urban expansion could also have an impact on this feedback loop, altering this relationship and making future projections even more challenging. We now have the model infrastructure in CESM to model dynamic urban expansion, as I believe Kuar, who's the next presenter, will talk more into. And the AC adoption modeling, on the other hand, requires some work. The current AC adoption is modeled by a proxy set point, which means there's not really a parameter that says how much percentage of buildings would have AC in this area, but instead, if this place has, say, low AC adoption, the interior thermostat set point would be set really high to reflect that the AC only runs under very hot days, which approximate the effect that not a lot of buildings have AC in this area. As you can see, this works for current projections for current state, but it's hard to extrapolate. It's hard to make future projections. And it's not very physically interpretable. This is why we wanted to add an explicit AC adoption rate parameter and set all buildings to a saturation set point, which is much more realistic and closer to what we experience in buildings. This way, the models can be easily fed with future AC adoption rate projections for us to investigate how socioeconomic factors and climate change would interact. So far, the co-development part has been done. We have the infrastructure ready, and we're developing the AC projection data sets for the whole globe to be used with this model. This is a summary of my presentation today. We see how climate HEC feedbacks elevate the uncertainty, nonlinearity, and spatial variability in climate-driven HEC energy demand projections, and we're working on incorporating socioeconomic factors into our projections. With that, I conclude my presentation. Thank you so much for your attention. I welcome questions and comments.
Thanks, Kathy. I saw that Keith raised his hand. Go ahead, Keith.
No, I was trying to clap, sorry.
Thank you.
Other questions? Yeah.
There's a ton of cool stuff that you guys are doing. It's really fun to see. And I think I just must have missed it in all the interesting results, but it seemed like your air conditioning energy flex was exponential, whereas the changes from heating went down linearly. And I didn't understand why the shape of those curves was different.
Yeah, that's a great question. I think I'll go to the schematic diagram for explaining this. As you can see, the feedback between a warmer urban environment and and AC is positive. So the process is warmer urban, more AC use, even warmer urban, and then it goes on. This explains why it increases non-linearly and almost exponentially. Whereas heating, it's sort of the other way around, where the more you use heating, the more waste heat is released to warm the urban environment, and in turn you can use slightly less heating to satisfy your heating demand. And this is the reason we observe this shape here. That's why we think the feedback regulates sort of the heating demand decrease, and it behaves closer to what the temperature is behaving. Does that answer your question?
Yeah, totally. Thank you.
Thank you.
So for the AC adoption, I'm curious how you kind of come up with the parameterization or the formulation for, I think you had something about climate factors and income factors. Are those the two main drivers for that?
Yeah, so there is quite a bit of literature out there that studies how AC adoption changes based on different factors, and it is mostly strongly correlated with income and climate. So for a place that is more affluent, people tend to have air conditioning in their home. And similarly, for a warmer place, uh, most most people with sufficient income will install AC. So this relationship we're going to use will come from a paper. I believe I have a slide here. So this is a paper we plan to use to model at least the 16 countries that the paper covered, where the adoption curve will be a function of household income and different cities, which represent different climate. And for places that are not covered, we plan to, because as a lot of you may know, there are 33 regions classified in CESM, urban model, and we plan to sort of broadcast these countries to their region, so they would share this adoption rate. And for regions that are not covered, we plan to use so inverse modeling, or we can look into the literature and see if there are case studies in those places that we can extract data or relationships from.
Yeah, thanks. And relatedly, I was also thinking about Charlie's question, which is what happens when people start switching to heat pumps. Have you guys thought about that at all?
That's again a great point, because heat pumps, if it's air sourced, well, it will be very similar to what we're modeling here, because we're assuming air conditioning having a coefficient of performance greater than 1, which is the behavior of a heat pump. But if it's a ground source heat pump, that affects ground temperature mostly. It doesn't affect as much the air temperature, but it's not something we could do with a simplified building energy model on a global scale yet, but it would be a very interesting future project if we want to look at the wide deployment of such technology and see how they affect urban climate and also energy. But yeah, that would be very interesting to see.
Okay, thanks. I think we'll move on. We have one more talk. Pierre Zhang is going to present on investigating direct and indirect impacts of global urban expansion on future climate. So you can go ahead and share your screen.
Can you see my slides well?
Yes, you're a little bit quiet, but we can.
Okay. What about now?
That's better. Yeah.
Okay. Yeah, I'll speak up then. So hi everyone, I'm Pierre Zhang, a PhD student at Yale University. I work with Professor Shihui Li, and today my presentation is about the direct and indirect climate effects of global urban expansion. So land use and land cover change has the direct and indirect climate effects. The direct effect refers to the climate response to the changes of surface properties like albedo. So it does not consider how atmosphere adjusts to the surface property changes. The indirect effect refers to the surface climate change because of the atmospheric feedbacks. And right now in current urban climate research, the local scale studies quantify the urban's impact as the contrast between urban and rural climate, assuming that urban and nearby rural lands share the same atmospheric condition. Therefore, it is only the direct climate impact. And only the regional scale studies consider both direct and indirect climate effects. They usually show that urbanization can change the regional circulation and cloudiness, and this atmospheric changes in turn will influence the air temperature. However, the direct and indirect climate effects of urbanization have so far never been discussed separately, and the previous simulations also can only use fixed urban surface, while the realistic urbanization is really dynamic. Therefore, here we would like to use the CESM2 with a new dynamic urban scheme to investigate how large are the direct and indirect climate effects of global urban expansion and what drives them. So this dynamic urban scheme updates the global urban land cover annually by reading the land use time series file. So here we firstly generated a new land use time series data set with the transient urban information. Here, two data sets are used. One is developed by our colleagues from the Beijing Normal University, so it's also called the BNU urban data, and another is from Gao and O'Neill 2020. So under the SSP5 scenario, the main differences between the two data sets is that Gao and O'Neill urban data has a much faster urbanization, and it provides urban land cover until 2100, but BNU urban data set only provides data until 2070. And here, these are the increases of the urban fraction in 2070 for the BNU data and in 2100 for Gao and O'Neill data set. We can see that most urbanization occurs in places where the cities already exist, such as East US, European, East Asian, and Indian. So initially, we only used the BNU urban dataset. We performed a pair of fully coupled simulations under the SSP5 RCP 8.5 scenario, one with constant urban surface at 2015 and another with dynamic urban from 2015 to 2070. And since the fully coupled simulations can capture all the interactions between different modal components, their differences include both direct and indirect climate effects of urbanization. And then two land-only simulations with and without urbanization were run. Since they are forced by the same atmospheric forcing, their differences really are just the direct climate effect of urbanization. And finally, the total effect minus direct effect is the indirect effect. Here we performed 3 ensembles for each experiment to reduce climate internal variabilities. And then we conducted another 4 simulations with the same setup, except for using the Gao and O'Neill urban dataset as a much stronger urbanization scenario, but only 1 ensemble is finished because of our limited computational resources. So here are the results. This map shows the direct climate effect on air temperature using the ensemble mean summer results from the BNU simulations. You can see that the direct climate effect increases air temperature by only 0.01 to 1 degree Celsius. And we found that the direct effect of urbanization can be predicted by this urban fraction increase and the state contrast between urban and rural lands in the grid. Because in cell M, the parameterization of urban subgrid climate state, it's not really influenced by urban state, by urban size. So no matter when the urban fraction is 25 or 50%, the urban and rural air temperature will actually not change as long as the atmospheric forcing and land properties are the same. And we know grid level air temperature is the area weighted mean value of all subgrids. So we can derive this expression of delta air temperature induced by direct effect as delta urban fraction times the urban minus rural air temperature. This delta TA predicted by the equation is actually nearly the same with the modeled direct climate effect on the air temperature. And similarly, we can also use this equation to predict the direct climate effect on vapor pressure, sensible heat flux, and latent heat flux by replacing here the air temperature with other variables. And meanwhile, these scatter plots also show that the direct effect is to increase air temperature and sensible heat flux, but decreases vapor pressure and latent heat flux. Then let's compare the direct and indirect climate effects. So this map shows the indirect effect on air temperature. And this map shows the direct effect using the same color scale here. We can go over again. Indirect impact, direct impact. So we can see that the direct impact changes the air temperature by negative 1.2 to 1 degree Celsius. So it's much larger than the direct effect. And we also notice here that the air temperature tend to increase for most regions with strong urbanization, like East US, East Asian, Indian, and coastal Africa. Here we can conduct a t-test on the indirect climate effect based on the 3 ensemble results we have. And then we found that the indirect climate effect is only significant in part of North America, as denoted by these dotted areas. This is because the indirect effect is influenced by random climate internal variabilities, and obviously here 3 ensembles are not enough to exclude all the impacts of internal variabilities. So at this point, we changed our analysis strategy here. Maybe it is difficult to accurately quantify the grid level indirect impact, but we probably still can reveal the mechanism of the indirect effect of urbanization. So next, we proposed this diagram to explain the air temperature change. We already know that direct effect of urbanization is to sort of increase air temperature and sensible heat flux and decrease vacuum pressure and latent heat flux. And then under the sum of direct and indirect climate effects, we firstly found that urbanization decreases the grid level relative humidity. But here, the key issue really is whether the decrease in relative humidity is induced by urbanization instead of internal variabilities. So to show this, we divide the global grids by its urban fraction change into these 4 groups. And here, the blue box plot shows the 10-year variations of group mean relative humidity changes between the fully coupled simulations with and without urbanization. And here, the black box plot shows the climate internal variability estimated from the 3 BNU ensembles. And finally, this blue bar is the differences of mean delta relative humidity between the blue and the black box plots, or the urban signals. Here, the pentagrams mean that the differences between the 2 box plots are statistically significant. So we can see that as the urbanization gets stronger, the urban impact becomes more negative, but the internal variabilities really remains relatively stable. So the urban signals are significant as delta urban fraction is larger than 1, and it means that areas with stronger urbanization do have significantly lower relative humidity, and this is not induced by climate internal variabilities. And then it's not surprising to find that changes in relative humidity is closely related to the cloud fraction change. Here, this is the vertical meridian profile of the relative humidity change, and this is the cloud fraction change. We can compare these 2 patterns. So they are very similar, especially at levels below 700 hectopascal, corresponding to the low cloud level. And then we actually also plot a scatter plot and found that the 2-meter relative humidity change and the low cloud fraction change are positively correlated. So here we can also see that urbanization decreases the cloud fraction while reducing relative humidity. And finally, we found that the decreased low cloud increases the downward all-way radiation, and then that changes the near surface temperature. So firstly, the changes in the low cloud fraction and the downward all-way radiation have very similar patterns, but reversed signs. We can come back and forth. This is because less low cloud usually decreases downward all-way radiation, but increases the downward shortwave radiation, and the shortwave radiation always increases more. So if we look at East US and East China here with strong urbanization, we can find that decrease the low cloud always increases the downward all-way radiation. And the changes in downward all-way radiation drives the 2-meter air temperature change. We can go back and forth and can see that their maps resemble each other very much. We actually found that the downward all-way radiation minus the reflected shortwave radiation has a very good positive linear relationship with air temperature change, but still the major driver here is the downward all-way radiation changes. But considering the reflected shortwave radiation improves the linear relationship a little bit. Here, the color represents the urbanization level. So red scatters have stronger urbanization, and they are more likely to have positive air temperature changes. And finally, we can use the same plot, the bar plot and the box plot and bar plot here to show the urban signals that is measured by the changes in air temperature. So you can see that urbanization, as the urbanization gets stronger, the changes in air temperature induced by urbanization also becomes larger, and still the urban signals are significant when delta urban fraction is larger than 10. Yeah, this is our major conclusions. And with that, I will be happy to take any questions.
Questions? I have a question about those maps that you were showing, actually, because some of the most significant changes looked like they were over Canada, which is not a place that I think with a lot of urban areas, but is that like a teleconnection, or is that due to how urbanization is changing over time. And yeah, can you talk about
Yeah, that's a good point. Actually, when we first analyzing these results, we were also puzzled about the negative delta air temperature over Canada, and it's also a very significant signal. So there are two possible sources for this air temperature change. One is possibly it comes from climate internal variability, and another possible reason, as you said, is because of teleconnection, because the indirect impact can not only influence the local grids with urbanization, it can also possibly change the air temperature for grids far away, even though they have no urbanizations. But perhaps I should say this in the beginning. If you look at this regional impact of air temperature, you can see that for this group with very weak urbanization, the total urban impact is very small for this group. So this total impact is the sum of climate internal variability and the possibly teleconnections. So they are either the two offset each other, or both of them are very small. Currently, I think it's very difficult to separate the two with our current results. So we are not really focused on the remote indirect impact of the teleconnection right now, and we are really focused on the local impact of indirect impact, local indirect impact. And also this diagram perhaps is more of a explanation for the local indirect impact. Yeah.
Okay, thank you, Abby.
Thank you.
Yeah, this was very cool. I was wondering, I'm sure you said, but I might have missed it. What did you do with the ocean? What kind of treatment did the ocean have, and how long were your simulations? Might help answer some of those last two questions.
I used interactive ocean. The model, I think it's called, the short name is POP. I'm not sure if I remember that correctly, but it's interactive ocean. And the simulation runs from 2015 to 2017. Yeah. Did you mean like how long did we spin up the simulation, or?
No, that's helpful. And then you did multiple ensemble members, so you can use that for the internal variability also.
Yeah.
Yeah, Claire?
I was wondering if when you were looking at the all wave, downwelling all wave, I think it was, whether you were looking out the cloud radiative effect from clear sky, just might be interesting to see the different mechanisms that were activated there. So I was curious if that's something you've looked at.
Yeah, we examined the changes of the downward all-wave radiation, also the changes of downward, long-wave radiation, short-wave radiation, and we also output the cloud impact on long-wave and short-wave radiation. And here I only shows the downward all-wave radiation, but when we analyze the cloud impact of the long-wave and the short-wave radiation, we found that the changes of the downward all-wave radiation largely comes from the cloud impact. And the impact is to increase the downward all-wave radiation. Is to increase the downward long-wave, decrease the areas with decreased low cloud have increased long-wave radiation, has decreased the long-wave radiation but increased the short-wave radiation, and that largely comes from the cloud impact. Yeah.
Thanks. There's a question from Jackie in the chat about the other data set, GAU, has very different patterns. Do you have predictions on that ensemble?
GAU, I'm not sure I've seen this name before. Do you know the full name of the data set?
It's possible that it was BAU? BNU?
And you mean the BNU data set has different patterns for the air temperature change? Do you mean?
Jackie, can you possibly?
It sounds like she means the two that you mentioned at the beginning. Do you have guesses as to what the other one will look like, because it is a different spatial pattern?
Oh, you mean, right. you mean the data set, urban data set? Is that right?
Yeah, I think so.
We'll come up with something. Sounds like a question.
We did not run simulations on the GU on urban land cover because we did not have enough computational resources to run multiple simulations based on different urban land cover. Yeah, but I think definitely with different urban land cover projections, we probably will get different patterns for the indirect impact, and also the because the urbanization may also have different teleconnections, so the results will be very different. But still, I think the key, I guess the key finding here in this study is that we kind of want to reveal what is the physical mechanism that really that can explain the indirect impact. So yeah, we did not run that. We did not run another ensembles using different urban land cover, but the underlying mechanisms should be consistent if we run another simulation, I think.
Yeah, Peter, go ahead.
I was just wondering, what was the analysis window you used? Was it 2060 to 2070 for the 3 ensemble members?
It's the last 10 years. So
Right.
that's 2071 to 2060. Yeah.
Do you think if you did compare that to 2050 to 2060, you might be able to get more statistical robustness? Even though you've got a slightly different climate period and slightly different urbanization, you'd still be able to do this without doing more runs. You'd maybe have more to see whether that result that you see in the teleconnections is stable for a different window.
Yeah, that's a good point. Actually, we tried to analyze this data set using like the last 10 years, the last 20 years, and even the last 25 years. But unfortunately, the signals are still not significant for most other areas. And I think when we are using a different simulation windows, like using the last 20-year results, we got pretty similar areas with significant urban signals. It's still the North. It's still the North American part. Yeah. But,
Thanks.
yeah. Thank you.
Okay. Yeah. Thanks so much. Yeah. Let's thank all our speakers from these sessions.
Great, thanks. Yeah, thanks everyone for a great session today.
Yeah.
And Southern Sun was busy yesterday, so since we're done a little early, if people are interested in going to Under the Sun this evening, I'd suggest maybe we get down there sooner rather than later. I think they're gonna hold 2 tables for us because 25-ish people said they were going. We probably just need to coordinate rides, so if people have vehicles and can offer rides, maybe I'll ask them, who needs a ride down the hill that's planning on going?
It's also the shuttle.
And who has a vehicle that could maybe take somebody? Okay, so if you need a ride, look at who has, keep your hand up to I'll let you self-organize and figure out who you can ask to get a ride down there. So it's, I don't know, 20 till now, maybe we can plan on being down there in 15 or 20 minutes or so. Yeah, and like, I haven't planned anything other than pick up beers and there's food. So if people want to stay for dinner, that's great. If you just want to have a snack and a drink, that's fine. But I think it'd be nice to continue the conversations that we've had today in a less rigid setting. Thank you. Tomorrow, I think we start at 8:30 again for BBC.